What if the universe's origin story, the one you think you know, is missing a crucial chapter? For decades, cosmologists like Alan Guth battled a universe that simply refused to make sense. Then a whisper, an idea so audacious, it reshaped creation itself. What was there before the symphony of existence began? Before the cosmic orchestra tuned its instruments? Before the first note of creation echoed through what would become space and time? There was nothing. Or was there? This is not merely an absence, a blank slate for creation to begin. This is a profound, ineffable quiet, so utterly complete that even the concept of nothingness struggles to take root. To truly grasp it, our minds must grapple with a paradox. How can something be before time, outside of space, devoid of matter, yet hold the very blueprint of all that would ever be? Our intuition forged in a universe of tangible objects and relentless motion rebels against such a thought. We instinctively seek a container for the void, a vessel for emptiness. But in this true beginning, there was no vessel, there was no where. The very notion of location of coordinates of up or down, left or right, was yet to unfurl its vast tapestry. There was no when for time itself. That relentless march of moments had not yet begun its first tick. Before the stardust began its grand cosmic ballet, before galaxies blossomed like celestial gardens, before the very laws of physics asserted their immutable decree, there existed only this primordial state, a realm beyond human comprehension, an unfolding silence that preceded everything. Physicists, those bold cartographers of the cosmic frontier, dare to peer into this abyss. They ask with a blend of scientific rigor and poetic awe what lies at the very boundary of existence. Was it an absolute vacuum, a perfect, unchanging emptiness? Or was it something far more intricate, more vibrant, more pregnant with possibilities than our everyday experience allows us to conceive? Imagine, if you can, a seething quantum foam, a bubbling cauldron, where virtual particles flicker in and out of being a universe not yet born, but brimming with the latent potential of every star, every planet, every living thing that would ever emerge. This is not the quiet of a still pond, but the profound silence of a universe, holding its breath on the precipice of its first magnificent exhalation. Consider the profound simplicity of it, a state without form, without dimension, without energy, yet from which all form, all dimension, all energy would ultimately spring. It challenges our deepest philosophical underpinnings. For what does it mean to be when there is nothing to be? How can a universe of such staggering complexity, a cosmos that sprawls across billions of light years, trace its genesis back to something so utterly devoid of discernible features? This is the paradox at the heart of the void. It is the ultimate expression of the simplicity-complexity paradox, where the most fundamental state, seemingly featureless, held within its ineffable quiet, the seeds of an infinite, intricate unfolding. This primordial stillness was not dead or inert. It was in its own mysterious way alive with possibility. It was the ultimate blank canvas awaiting the first stroke of creation, a stroke that would ignite the cosmic crucible and set in motion the grand narrative of stars and singularities. It was the initial whisper of eternity, the cosmic nothing, that paradoxically contained everything. It was the ultimate beginning, not with a bang, but with an echoing, ineffable silence waiting for the cosmic dawn. And in this boundless void, holding within it the blueprint for all that would ever be, we find the genesis of our story poised on the brink of an awakening that would forever change the face of existence. This was the quiet before the chaos, the calm before the storm of creation. It was the profound, resonant silence from which all sound, all light, all life would ultimately emerge. It was the universe's greatest secret held in the deepest, most inaccessible reaches of pre-existence. The stage was set not with tangible elements, but with their profound and eloquent absence, waiting for the moment when the first quantum flicker would ripple through the boundless nothingness, the absolute quiet. The profound, ineffable stillness that Chapter 1 invited us to contemplate. A void so complete, so utterly devoid of all things, that even the concept of nothingness struggled to take root. It was the ultimate before, a boundless canvas awaiting its first brushstroke, a silent symphony poised on the precipice of its opening note. For an eternity, or perhaps for no time at all, for time itself, had yet to be conceived a dimension waiting to be woven into existence. This unfathomable potential lay dormant. A universe pregnant with possibilities yet to be born, holding within it the silent blueprint for all that would ever be. Then, approximately 13.8 billion years ago, the silence shattered. Not with a conventional sound, for there was no medium to carry a wave, no ear to hear it, but with an event so cataclysmic, so fundamentally transformative, it remains the ultimate Genesis story. We call it the Big Bang, the moment of becoming. This term, however, is often profoundly misunderstood, conjuring images of a conventional explosion, a blast scattering debris into an already existing cavernous emptiness. But dismiss this notion entirely. This was no such blast into space. This was the universe itself, not merely born, but becoming as the very creation and expansion of space-time matter and energy from a state beyond human comprehension. Imagine if your mind can stretch that far all the matter and energy of our colossal cosmos, every star, every galaxy, every planet, every atom, every particle, compressed into a point immeasurably smaller than even the nucleus of an atom. An infinitely dense, infinitely hot singularity. Here at this cosmic crucible, the very laws of physics as we understand them simply break down. This is where the curvature of spacetime becomes formally infinite, a mathematical infinity that signals the limits of our current theories. It is a realm where our equations falter, where human intuition offers no grip, where cause and effect lose their meaning. This infinitesimal point, this cosmic seed beyond all comprehension, held within it the entirety of our future reality, a universe coiled into an impossibly compact form. The initial fleeting moments following this cosmic awakening were a whirlwind of unimaginable intensity. This was the Planck epoch, an era so infinitesimally brief, a mere 10 to the negative 43rd seconds, that's a decimal point followed by 42 zeros, before a 1 that it exists at the very boundary of our current scientific understanding. To put it into perspective, light, the fastest thing we know, could only travel a distance far, far smaller than a proton in that unfathomable flicker of time. In this unimaginable flash time began its relentless march, and space unfurled from that primal point, expanding at a rate that beggars belief. What were the conditions like extreme beyond measure? The universe was a seething, churning soup of pure energy, a plasma of such incredible density and temperature that even elementary particles could not yet coalesce. It was a place where the four fundamental forces that now govern every interaction in the cosmos, gravity, electromagnetism, and the strong and weak nuclear forces, were not distinct entities. They were perhaps unified, a single, all-encompassing superforce, weaving the very fabric of reality with a single, elegant, overarching thread. This state of profound unity, often called the grand unified theory in theoretical physics, is a holy grail of modern cosmology, hinting at a sublime simplicity underlying all complexity. This was the universe as pure potential, a boundless canvas ready to be painted, its foundational laws still coalescing from a state of primordial oneness. It was a realm where the mind-bending principles of quantum mechanics danced with the majestic curvature of general relativity in a cosmic ballet we can only glimpse through the most sophisticated theoretical veils. A moment of breathtaking beauty and terrifying power where the very essence of existence was forged. From that boundless void, from that searing singularity, the cosmos became a silent blueprint transformed into a roaring, incandescent reality. And in that becoming, the seeds of everything, stars, galaxies, planets, and even the intricate dance of life itself were sown, waiting for their turn to unfold on the grand cosmic stage, forever expanding, forever evolving. Imagine Professor Eleanor Vance, decades ago, hunched over stacks of cosmological data, a single stubborn question gnawing at her. She traced the exquisite, near-perfect uniformity of the cosmic microwave background, that ancient light echoing from the universe's infancy. How could distant corners of the cosmos regions, so vast and separated they should never have had time to talk to each other, possess almost identical temperatures? It was like finding two strangers on opposite ends of a vast continent, wearing perfectly identical custom-made garments, having never met, never exchanged a word. It defied causality, challenged the very notion of cosmic logic. And then the universe's geometry. Why was it so uncannily flat, like a meticulously ironed sheet, instead of curving into a sphere or a saddle? The odds were astronomical against such a precise balance. These were the universe's most profound riddles, its most frustrating paradoxes, whispering discontent into the ears of every cosmologist. From the searing crucible of the Planck epoch, a realm of unified forces and unimaginable density, the universe was not destined for a slow, stately unfurling. Instead, a cosmic whisper barely audible above the echoes of creation began to resonate. It was not a gentle sigh, but the prelude to an exponential burst, a growth so rapid it defies common sense, a quantum leap in the universe's nascent existence. This was the moment approximately 10:32 seconds after the Big Bang, when the universe underwent a phase known as cosmic inflation. This audacious idea, spearheaded by brilliant minds like Alan Guth, offered a radical solution to those perplexing paradoxes. Dismiss the image of a balloon merely expanding. During inflation, the universe didn't just expand. It ballooned, exponentially growing by a factor of at least 10^26 in that infinitesimal fraction of a second. To put that into perspective, imagine a single atom suddenly inflating to become larger than our observable universe. This superluminal expansion, while seemingly breaking Einstein's cosmic speed limit, was not the movement through space, but the expansion of space itself. This was not matter hurtling faster than light through a pre-existing void, but the very fabric of space-time itself stretching, pulling apart, expanding on its own terms. The elegance of inflation lay in its profound solutions. The horizon problem, the bewildering uniformity of the cosmic microwave background, was smoothed away. Before inflation began its furious stretch, all the regions that now appear causally disconnected were in fact incredibly close within causal contact. They had time to exchange information to reach a uniform temperature. Then inflation ripped them apart, stretching that perfect uniformity across the vast cosmic canvas, presenting us with the smooth, consistent CMB we observe today. And the flatness problem. Inflation resolved it with similar grace. Imagine taking any curved surface like a crumpled piece of paper and stretching it to an unimaginable extent. As it expands, any initial curvature becomes infinitesimally small, making the surface appear perfectly flat on our observable scales. Inflation took the universe, no matter its initial curvature, and stretched it so immensely that the geometry we perceive today appears astonishingly, almost impossibly flat, just as a small patch of a gargantuan sphere would seem flat to an ant. This whisper of inflation, an ephemeral but unimaginably powerful force, laid the homogeneous foundation for the cosmic structures we see today. It ironed out the wrinkles, equalized the temperatures, and set the stage for the universe to evolve into the vast, intricate cosmos we inhabit. It was a moment of profound transformation, taking a universe pregnant with potential and preparing it for the unfolding drama of matter energy and the eventual dance of galaxies. The stage was set, the initial conditions refined by this fleeting explosive expansion, ready for the next act of cosmic creation. Following the brief, furious burst of cosmic inflation, that unimaginable exponential expansion that shaped the universe's earliest geometry, the cosmos continued its rapid unfurling. Yet this expansion was now at a more leisurely, albeit still incredibly fast pace, allowing the universe to begin its long, slow process of cooling. This transformation from an unimaginable inferno was the crucial next step, leading to the formation of a seething primordial soup of fundamental particles and energy. This epoch, lasting until roughly 1 second after the Big Bang, was dominated by what physicists call the Quark-gluon plasma. Imagine a state so hot and so dense that even protons and neutrons, the stable building blocks of atomic nuclei that form everything around us, could not yet exist. Instead, their constituent parts, the elusive quarks, and the powerful gluons that bind them, danced freely unbound in a chaotic, swirling maelstrom. It was a universe truly governed by the raw, untamed power of the fundamental forces, a realm where matter and energy were almost interchangeable, converting back and forth in a ceaseless high-energy ballet. Gravity, already at play since the Planck epoch, subtly began to sculpt the nascent cosmos, its gentle, pervasive tug laying the groundwork for future structures. The strong nuclear force, the binder of quarks, and the most powerful of the fundamental interactions, was still too weak to overcome the immense energies and bind quarks into stable particles. The weak nuclear force, responsible for radioactive decay and particle transformations, facilitated a delicate balance, converting protons into neutrons and vice versa, influencing the initial elemental abundances that would soon be forged. Electromagnetism, too, began to emerge, influencing the charged particles that darted through the superheated plasma, contributing to the universe's overall opacity. This was a universe truly in its infancy, tumultuous and opaque, a dense fog of pure energy and light. In this chaotic environment, energy spontaneously converted into particle-antiparticle pairs, electrons and positrons, neutrinos and antineutrinos, only to annihilate each other in brilliant flashes of energy. This cosmic dance of creation and destruction maintained a delicate balance, a fleeting equilibrium driven by the extreme temperatures. As the universe continued to cool ever so slightly, the rate of particle production began to drop below the rate of annihilation, leading to a slight asymmetry. For every billion particle-antiparticle pairs that annihilated, approximately 1 particle of matter remained. This tiny, crucial imbalance, perhaps originating from some subtle violation of symmetry at even earlier, more energetic times, is the fundamental reason why our universe is filled with matter at all, and not just a sea of radiation. Without this infinitesimal surplus of matter, we and everything around us would not exist. It was the universe's first step towards the complexity we inhabit, a subtle shift in the cosmic ledger that paved the way for all future existence, slowly transforming from pure energy to the earliest forms of mass. The stage was set for the next grand act in the cosmic drama. Imagine, if you will, not the clanging of steel on anvil, nor the acrid smoke of a blacksmith's shop, but a forge of immeasurable scale, hammered into existence by the very fabric of space-time itself. The searing, opaque fog of the Quark-gluon plasma, that tumultuous maelstrom described in Chapter 4, began its inevitable transformation. As the universe continued its unfathomable expansion, each fleeting moment stretched the cosmic canvas further, thinning its density and crucially shedding its incomprehensible heat. This wasn't merely cooling. It was a cosmic exhalation, a slow, deliberate drawing down of the primordial inferno, paving the way for a monumental genesis. Within the first few minutes after the Big Bang, a critical threshold was crossed. The energies once so colossal they ripped apart any nascent structure, now softened just enough. The raw, untamed power of the strong nuclear force, the mightiest of the four fundamental interactions, could finally begin its work. No longer were the quarks and gluons mere unbound dancers. They found their partners cohering with exquisite precision into the very first stable protons and neutrons. These particles, the nascent kernels of all future matter, hovered in a delicate balance, their existence fleetingly secured by the dwindling chaos, yearning for a deeper, more profound union. It was an alchemist's dream, on a universal stage where the ingredients for stars themselves were being prepared in an unearthly crucible. This monumental period, known to cosmic archaeologists as Big Bang nucleosynthesis, or BBN, commenced in earnest. It was the universe's primordial forge, operating at temperatures still billions of degrees, but now finally cool enough for bonds to form. The dominant proton, a solitary hydrogen nucleus, became the first participant. In a dance of creation that defies our everyday intuition, these protons colliding with newly formed neutrons fused. Not with a whimper, but with the silent thunder of cosmic creation, they forged deuterium, a heavier isotope of hydrogen possessing one proton and one neutron. Each such union was a victory against the dissipating energy, a small step towards the complex universe we inhabit. The newly minted deuterium was but a stepping stone. Like restless seeds, these nuclei sought further companionship. They fused again, either with another proton, or a neutron, or even another deuterium nucleus, building ever so slightly more complex structures. The next milestone was helium-3, with its 2 protons and single neutron. But the ultimate target, the most stable and significant product of this epoch, was helium-4, composed of 2 protons and 2 neutrons. This was the universe's grand masterpiece of these first 20 minutes, an abundance of stable hydrogen and helium, the raw ingredients for its future stellar nurseries. Only the barest whisper, a cosmic trace element of lithium-7, with 3 protons and 4 neutrons, also sputtered into existence. Beyond that, the door to heavier elements remained firmly cosmically shut. Why, you might ask, did this extraordinary epoch of elemental creation cease so abruptly? Why didn't the cosmos continue its alchemical work, forging carbon, oxygen, or the iron that courses through our veins? The answer lies in the relentless march of the universe's most fundamental property, expansion. The cosmos was expanding and thus cooling at a rate so staggering that the window for fusion, though lasting 20 minutes in our human perception, was fleeting in cosmic terms. The densities of protons and neutrons plummeted too rapidly. They simply became too far apart, and the ambient temperature dropped too low for further significant nuclear reactions to occur. The strong nuclear force, though powerful, could no longer overcome the vast distances and insufficient energies to bind more complex nuclei together. The universe had its initial recipe, a simplicity born from complexity, and then it moved on. The legacy of this fleeting, furious period is not just a theoretical construct. It is demonstrably etched into the very fabric of reality, a profound cosmic archaeology. When we gaze at the most ancient stars, those cosmic elders born from the pristine gas clouds of the early universe, we find their composition to be precisely what Big Bang nucleosynthesis predicted: approximately 75% hydrogen and 25% helium, with only minute trace amounts of lithium. This ratio, this primordial cosmic recipe, serves as one of the most compelling pieces of empirical evidence for the Big Bang model itself. It's a consistent, verifiable fingerprint observed in the furthest reaches of the cosmos, in the light from distant gas clouds, pristine and untouched by stellar processes. From the silent, unknowable void of Chapter 1, through the cataclysmic becoming of Chapter 2, the inflationary whisper of Chapter 3, and the awakening chaos of Chapter 4, we now see the first tangible building blocks. A universe awakening not just into existence, but into a specific, measurable composition. This cosmic census of elements taken mere minutes after time continues to inform our understanding, reminding us that even the most fundamental components of our world are ancient echoes of a dramatic, violent birth. The universe began as an abstract potential, evolved into a plasma, and then, in a blink of cosmic time, forged the very lightness of being. Even after the initial burst of Big Bang nucleosynthesis, which forged the universe's primordial supply of hydrogen and helium, the cosmos remained a profoundly alien and mysterious place. For nearly 380,000 years following the Big Bang, the universe was shrouded in a thick, impenetrable fog. It wasn't a fog of water vapor, but a superheated ionized plasma, hot enough that electrons remained stubbornly unbound from atomic nuclei. Imagine the universe as a vast glowing crucible, where charged particles free electrons and atomic nuclei roiled in chaotic motion. In this dense, electrically charged soup photons, the very particles of light found themselves utterly trapped. Every time a photon attempted to traverse this cosmic plasma, it would almost immediately scatter off a free electron, much like trying to navigate a bustling, overcrowded marketplace where everyone is constantly bumping into you, preventing any clear path. This incessant scattering meant that light simply could not travel freely across the cosmos. The universe, in essence, was entirely opaque to light, its vastness illuminated only by the constant ephemeral flashes of scattering. No stars existed yet to produce light of their own, and any faint glow that originated from the Big Bang's afterglow was instantly absorbed and re-emitted, never truly traversing the vastness to reveal any underlying structure or form. This era, known as the photon epoch or the plasma era, was a time of pervasive, fundamental darkness, literally. While the universe was indeed incandescent with the energy of its birth, that energy was trapped, unable to propagate or reveal anything beyond its immediate chaotic vicinity. It was a cosmic veil, impenetrable and all-encompassing, a period of immense significance, precisely because it set the stage for one of the most crucial cosmic revelations to come, the moment light would finally break free. This was a lull in the cosmic narrative, a period of waiting, of incubation, where the universe, still relatively uniform, was slowly expanding and cooling patiently, approaching the critical temperature and density that would allow for the next great transformation. The dense, opaque conditions meant that any primordial structure was effectively smoothed out, hidden from view, awaiting the moment when the cosmic veil would finally lift and reveal the nascent universe within. This period, in its profound obscurity, was a testament to the universe's evolving nature, a necessary precursor to the clarity and complexity that would eventually emerge. For nearly 400 millennia, the cosmos had remained a profound enigma, a realm shrouded in its own nascent being. As Chapter 6 recounted, the universe was a dense, electrically charged fog, a roiling plasma where photons, the very particles of light, were trapped, unable to journey more than an infinitesimal distance without colliding with a free electron. It was a universe blind to itself, an opaque, tumultuous cloud that swallowed nascent light before it could even begin its voyage. But like a chrysalis shedding its final layers, the universe was on the precipice of a monumental transformation, an event that would pull back the cosmic veil and allow the first true light to stream across the emerging canvas of space. Imagine, if you will, the universe's temperature relentlessly dropping a slow, inevitable cooling from the cataclysmic inferno of its birth. For 380,000 years, this immense heat had kept electrons violently ripped from their atomic nuclei, creating that ubiquitous light-trapping plasma. But the laws of physics, unrelenting in their march, dictated a critical threshold. As the expansion continued, its steady, albeit still incredibly rapid pace, the temperature of the cosmos finally dipped below approximately 3,000 Kelvin. To put that into human perspective, this is roughly the temperature of the surface of a cool star, like a red dwarf. Still intensely hot, but a dramatic cooling from the earlier unimaginable furnace. At this precise, pivotal moment, the universe underwent what cosmologists call recombination. It sounds counterintuitive, doesn't it? Recombination, when it was the first time these particles had ever truly combined. It's a term born from the idea that in the grand scheme of things, these elements could eventually recombine. The sheer kinetic energy that had once kept electrons violently unbound from their proton and light nuclei counterparts simply wasn't strong enough anymore. The electromagnetic force, which governs the attraction between charged particles, finally asserted its dominance. Electrons, once free-roaming vagabonds, were now captured, drawn into stable orbits around the newly formed hydrogen and helium nuclei, creating the universe's very first stable neutral atoms. This was no gentle whisper. It was a profound shift in the fundamental state of matter across the entire cosmos. With the formation of these neutral atoms, the universe was fundamentally, irrevocably changed. Suddenly, the vast sea of free electrons that had acted as incessant obstacles for photons, those endless cosmic bumpers, was gone, locked away within the newly formed atoms. This moment is known as decoupling, because light, once inextricably coupled to matter, was now free. The cosmic fog lifted. Photons, liberated from their eternal dance of scattering, were at last able to stream across the vast expanding void, unimpeded, hurtling through nascent space at the speed of light. This ancient light, now stretched and cooled by billions of years of cosmic expansion, is precisely what we observe today as the cosmic microwave background, or CMB. It is the universe's ultimate fossil relic, the faint, uniform glow of microwave radiation washing over us from every direction in the sky. It is literally the oldest light in the universe, a breathtaking photograph taken when the cosmos was just a tiny fraction of its current age, a mere 380,000 years young. When we gaze upon the CMB, we are not just looking back in time. We are looking at the universe's baby picture, a direct visual echo of its earliest, most formative moments. While the CMB appears remarkably uniform, testifying to the smoothing power of inflation as discussed in Chapter 3, closer inspection reveals tiny, crucial temperature fluctuations, variations of only a few parts per million. These aren't random noise. They are the profound imprints of the earliest density variations, the gravitational ripples, in that primordial plasma. They are the seeds, the almost imperceptibly tiny gravitational perturbations, from which all future cosmic structures would sprout. These infinitesimally small variations would over billions of years grow into the vast cosmic web of galaxies, clusters, and superclusters we observe today. The CMB is not just a picture, it is the blueprint. It is the universe's first grand revelation, the moment it unveiled its true, profound nature, whispering the secrets of its origin in a symphony of ancient light. Imagine a universe just moments after its first great unveiling. The brilliant, searing flash of the cosmic microwave background, a light born from the very fabric of existence, has just streamed away, journeying across the nascent cosmos. If you were a cosmic wanderer, perhaps a being of pure energy, or a spirit of nascent consciousness, floating in the vast expanse, what would greet your senses? Not the roaring inferno of earlier epochs, nor the shimmering majesty of galaxies yet to be. No, what would engulf you, and what truly dominated this new era, was an overwhelming, profound quiet. A darkness not born of chaos or violent occlusion, but of utter luminous absence. A void pregnant with unseen potential. This was the dawn of the cosmic dark ages, a vast and enigmatic stretch of time that began approximately 380,000 years after the Big Bang and endured for hundreds of millions of years until roughly 400 million years later. The universe had cooled sufficiently for electrons to finally surrender to the gentle yet powerful embrace of protons and light nuclei, forming stable neutral atoms of hydrogen and helium. This pivotal moment, known as recombination, had freed the primordial light, allowing it to decouple from matter and stream away unhindered. What remained was a cosmos profoundly transparent, yet hauntingly empty of self-generated illumination. The universe, stripped of its initial fiery glow, became a canvas of unparalleled homogeneity. Picture an endless, tranquil ocean perfectly still, devoid of waves, currents, or even a breath of wind. This was the cosmic sea, overwhelmingly composed of neutral hydrogen, making up about 75% of its baryonic mass, with a quarter of its ordinary matter as helium, and only the barest whisper of lithium. There were no stars, no galaxies, no luminous objects of any kind to pierce the pervasive gloom. The freed photons of the CMB continued their infinite journey outwards, leaving behind a cosmos that was paradoxically transparent to light, but possessed no new light sources within itself. It was the deepest quiet after the loudest roar. This era was a profound lull, a cosmic breath held after the cataclysmic birth and the furious forge of nucleosynthesis. It was a time of immense calm, a quiet incubation chamber, a cosmic chrysalis. The universe, having shed its plasma veil, was now a vast cold expanse stretching across billions of light years, featureless and seemingly inert. Yet within this deceptive simplicity, a profound and intricate process was quietly, inexorably unfolding. The universe, the patient architect, had begun its next grand design, unseen, unheard, utterly foundational. For even in the deep quiet, one force remained eternally active: gravity. This invisible hand, acting on the merest whispers of density variations, those infinitesimal fluctuations imprinted in the cosmic microwave background, mere parts per million in temperature, began its relentless sculpting work. Over hundreds of millions of years, gravity slowly, inexorably began to draw the neutral hydrogen and helium gas together. These slight overdensities, born from quantum fluctuations in the inflationary epoch, became tiny gravitational wells, subtly pulling in more and more surrounding gas, like an invisible magnet drawing iron filings. It was a process of almost glacial slowness, operating on scales far beyond human comprehension, completely unseen and unheard by any potential observer. There was no grand explosion, no brilliant flash of light to mark its progress. The gas did not condense into stars overnight. Instead, it slowly incrementally gathered into larger and larger clumps. These nascent structures, proto-halos of dark matter and ordinary baryonic gas, were the embryonic forms of galaxies and galaxy clusters, the future cosmic cities and superclusters. The universe was not empty, but pregnant with potential, silently gathering the raw materials, folding them in upon themselves with an unseen, patient hand. This apparent darkness was merely a profound patience, a necessary quiet before the first stars would ignite, shattering the cosmic veil and bringing light back to a patiently waiting cosmos, forever transforming its fundamental nature. Yet even in the pervasive, profound quiet of the cosmic dark ages, a period of apparent stasis and darkness that followed the universe's great unveiling, the cosmos was far from truly inert. Indeed, it was pregnant with possibility, containing within its vast uniform expanse the faint, almost imperceptible whispers of future cosmic grandeur. This underlying activity stemmed from infinitesimal variations in density and temperature. Tiny ripples left over from the incredibly rapid exponential unfurling of the inflationary epoch. These were the quantum fluctuations, microscopic quantum mechanical jitters present in the very fabric of space-time during the universe's explosive infancy. Imagine, if you will, a perfectly smooth, perfectly still surface, a cosmic canvas stretching billions of light-years. But upon closer, almost impossibly magnified inspection, you wouldn't find it perfectly uniform. Instead, you would discern tiny, almost imperceptible bumps and troughs, minute variations in the distribution of energy and matter. These subatomic undulations, born from the inherent uncertainty of the quantum realm, and then stretched across truly cosmic scales by the immense power of inflation, became the crucial seeds of all future large-scale structure in the cosmos. They were the primordial imperfections, ironically vital for the eventual beauty and complexity of the universe. In regions where the density was ever so slightly higher than average, even by a mere 1 part in 100,000 gravity, that patient and persistent architect would begin its slow, inexorable work. This slight excess of matter meant a slightly stronger gravitational pull, which over vast stretches of cosmic time would attract even more surrounding gas and dark matter. It was a subtle feedback loop, a gentle cascade. A little more matter meant a little more gravity, which pulled in even more matter, slowly accumulating more and more gas. These minute differences, initially mere fractions of a percent, were the embryonic knots in the cosmic tapestry. Over hundreds of millions of years, throughout the long, quiet interlude of the Dark Ages, these tiny density enhancements would gradually grow, patiently coalescing like snow gathering on the highest peaks into the colossal structures we observe today, the nascent clusters and filaments of galaxies. Without these primordial seeds meticulously sown in the earliest, most extreme moments of the universe's existence, and then stretched by inflation, the cosmos would have remained largely a featureless, utterly homogeneous void. It would be a bland, uniform sea of hydrogen and helium, eternally expanding, devoid of the intricate cosmic web, devoid of the gravitational wells necessary for stars to ignite, and therefore devoid of galaxies of planets and ultimately of the complex chemistry that gives rise to life itself. The presence of these seemingly insignificant initial conditions is a testament to the profound interconnectedness of the universe's history, where events occurring in the first split second dictate the grand architecture of billions of years later. It was in this quiet, unseen shaping that the universe began its slow march toward the vibrant, structured existence we inhabit, setting the stage for the next crucial, invisible player in its ongoing drama. Chapter 10. The Invisible Architect. The gravitational accumulation of matter initiated by quantum fluctuations was not solely the work of the familiar atoms and light we can see. A far more enigmatic force was at play, an invisible architect shaping the cosmos, dark matter. Comprising approximately 27% of the universe's total mass energy content, dark matter is truly a ghost in the machine. Unlike ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and US dark matter does not interact with light. It neither emits, absorbs, nor reflects any form of electromagnetic radiation. We cannot see it, we cannot touch it, and it passes through us and through entire planets unimpeded. Its existence is inferred solely through its gravitational pull. For decades, scientists like Vera Rubin observed that galaxies were spinning too fast. Their visible matter simply wasn't enough to hold them together. The only explanation was the presence of a vast unseen halo of mass exerting a gravitational tug, preventing these galactic superspinners from flying apart. Dark matter remains one of cosmology's greatest mysteries, yet its pervasive influence is undeniable, the invisible hand guiding the universe's grand design. Imagine a grand cosmic waltz, billions of dancers swirling in a symphony of gravitational forces. Now picture the most magnificent of these ballets, a galaxy, an island universe of hundreds of billions of stars, each one a luminous point in a vast spinning disk. For decades, astronomers observed these colossal structures charting their rotational speeds, and what they found sent ripples of profound unease through the scientific community. The visible matter, the stars, the gas, the dust, all the things that emit light simply wasn't enough. The luminous tapestry of suns by itself couldn't generate the gravitational pull required to hold these galactic superspinners together. According to the known laws of physics, these magnificent spirals should have long ago torn themselves apart, their outer edges flung into the lonely void of intergalactic space. This was the cosmic riddle that vexed brilliant minds for generations. How could something be there, yet not be seen? It was as if a conductor was orchestrating a performance, but remained entirely invisible to the audience. The universe, it seemed, was playing a trick on our eyes, revealing only a fraction of its true composition. This profound deficit of visible matter was not a flaw in our understanding of gravity, but a monumental revelation of the universe's unseen majority. An invisible hand, a pervasive ghost in the machine, was at work. This unseen entity, this ethereal architect, is what we now call dark matter. It makes up approximately 27% of the universe's total mass energy content, yet it remains one of the deepest, most enigmatic mysteries of modern cosmology. Unlike ordinary baryonic matter, the familiar protons, neutrons, and electrons that compose everything we can see and touch, from the smallest atom to the largest supercluster of galaxies. Dark matter does not interact with light in any discernible way. It neither emits, absorbs, nor reflects any form of electromagnetic radiation. We cannot see it with our most powerful telescopes, we cannot touch it, and it passes through us, through our very planet, and through entire solar systems, seemingly unimpeded. Its only known interaction, its sole undeniable signature, is its gravitational pull. The observational evidence for dark matter began to crystallize in the mid-20th century, notably through the pioneering and persistent work of Dr. Vera Rubin and her colleague Kent Ford. Through meticulous measurements of galaxy rotation curves, they observed that stars and gas clouds at the outer edges of galaxies were orbiting at unexpectedly high speeds. If visible matter were all there was, these outer regions should have been moving much slower, like the outer planets in our solar system. The only way to explain this discrepancy was the presence of a vast unseen halo of mass, far more extensive than the luminous disk, exerting a gravitational tug that prevented these galactic dancers from flying apart. Their work provided compelling, almost irrefutable evidence for something fundamental that was missing from our cosmic inventory. Remember the faint whispers from the cosmic dark ages, the tiny ripples in the cosmic fabric, the quantum fluctuations left over from the inflationary epoch, which were the seeds of all future structure. It was dark matter that amplified these whispers into cosmic roars. Ordinary baryonic matter bound by electromagnetism struggles to collapse quickly on its own. Radiation pressure and thermal motion resist the pull of gravity. But dark matter, oblivious to light, felt only the patient, pervasive tug of gravity. It formed vast, invisible scaffolds, immense gravitational wells into which ordinary matter could then slowly, inexorably fall. These dark matter halos, these cosmic webs of the unseen, provided the foundational framework for galaxies to clump together, for clusters to form, and for the large-scale structure of the universe to emerge from the primordial soup. Dark matter remains one of science's greatest puzzles, its true nature eluding our most sophisticated instruments and theoretical models. Is it a swarm of exotic, weakly interacting massive particles, or WIMPs theorized to barely interact with anything except gravity? Is it something even more profound, a warp in the very fabric of reality that we have yet to grasp? The hunt for direct detection of dark matter. Particles continues in deep underground laboratories, shielded from cosmic rays where scientists hope to catch the faintest whisper of a collision with an ordinary atom. Yet its pervasive influence is undeniable. It is the silent, omnipresent force that guided the universe's grand design from its earliest moments, the invisible hand shaping the cosmic structures we inhabit. The universe, as we increasingly understand, is not merely what meets the eye. It is a symphony composed largely of the unheard, a masterpiece, painted with invisible brushstrokes. Our journey into the cosmos is not just about what we discover, but what we learn to perceive beyond the obvious. And in the enduring mystery of dark matter, the universe continues to whisper its profound secrets, inviting us to listen, to observe, and to wonder at the unseen architects of our reality. Consider the greatest structures ever built by human hands, from the ancient pyramids, each stone precisely placed upon an unseen foundation, to the soaring cathedrals whose intricate spires rise from deeply rooted invisible supports. Imagine attempting to construct such monumental works without any underlying framework, without the hidden steel rebar or the foundational concrete. It would be an exercise in futility, a collapse before construction even began. So too did the nascent universe after its fiery birth, and the subsequent calming of the Dark Ages require its own colossal scaffold, an invisible pre-existing skeleton upon which all the shimmering galaxies and incandescent stars would eventually come to rest. We have unmasked dark matter as the universe's most profound enigma, a pervasive, unseen force whose gravitational signature is undeniable as revealed by the anomalous spins of galaxies. But its most ingenious role, its true genius, became clear during the profound quiet of the cosmic dark ages, that vast period of hundreds of millions of years when the universe was little more than a transparent expanse dominated by neutral hydrogen and helium gas. It was then, in this immense cosmic lull, that dark matter truly began its work as the universe's ultimate architect, not just an invisible force, but an indispensable pre-existing structure that would fundamentally shape everything to come. The secret to dark matter's pivotal role lies in two deceptively simple characteristics. It is collisionless, and it is cold. Let us unravel these properties, for they are the bedrock upon which the cosmic web was spun. Unlike the familiar baryonic matter, the protons, neutrons, and electrons that comprise everything we see and touch, which interacts furiously with light experiences, immense pressure, and constantly bumps into itself. Dark matter possesses a singular profound indifference. To be collisionless means that dark matter particles rarely, if ever, interact with electromagnetic forces, or even with each other beyond their mutual gravitational pull. Imagine trying to build with blocks constantly ricocheting off each other. Baryonic matter in the hot, dense early universe was precisely that, a volatile, energetic soup where any gravitational clumping was immediately counteracted by the outward pressure of radiation. But dark matter felt no such pressure. It remained utterly immune to the electromagnetic chaos, and to be cold means that dark matter particles move relatively slowly, allowing them to settle into gravitational wells rather than escaping them. If dark matter were hot, moving at relativistic speeds, its particles would have simply diffused away, unable to clump effectively. But its sluggishness, its inherent gravitational stillness, was a cosmic blessing. As the universe continued its relentless expansion and cooling those faint primordial ripples in density, the infinitesimal quantum fluctuations amplified by inflation, which we saw imprinted on the cosmic microwave background, began their slow gravitational work. In these regions where dark matter was ever so slightly more concentrated, gravity began its inexorable pull. Unburdened by interactions with light or thermal pressure, dark matter particles pulled on each other with singular efficiency, forming the very first significant structures in the cosmos' colossal spherical aggregations known as dark matter halos. These were not the bright visible galaxies we know, but vast invisible cocoons of mass, forming hundreds of millions of years before the first stars would even dream of igniting. They were the universe's foundational pillars, erected silently in the deep cosmic dark, awaiting their visible cladding. These nascent dark matter halos, these immense gravitational wells, then exerted a powerful, irresistible pull on the surrounding neutral hydrogen and helium gas, the very same diffuse baryonic matter that dominated the Dark Ages. Like cosmic magnets, the dark matter drew in the ordinary gas slowly but surely, concentrating it into the heart of its halos. This was the critical divergence, the moment when the universe truly began to transform. While ordinary matter, left to its own devices, would have struggled against its own internal pressures and the lingering heat from the Big Bang to form dense structures, dark matter provided the necessary gravitational anchor, a pre-existing skeleton that patiently coaxed the diffuse gas to gather. Without this invisible scaffold, the baryonic matter would have remained too spread out, its own self-gravity insufficient to overcome its thermal motion, and form the dense enough pockets required for star formation within the universe's current age. The implications of this invisible scaffolding are nothing short of staggering. Had dark matter not been cold and collisionless, had it interacted with light and other particles like ordinary matter, it too would have been prevented from collapsing early. The universe would have been a profoundly different place, a perpetually homogeneous, featureless expanse, perhaps devoid of the intricate cosmic web of galaxies, clusters and superclusters that defines our observable cosmos. It would have remained a silent, almost uniform canvas forever, waiting forever unpainted, with the vibrant star-studded structures we marvel at today. Dark matter, unseen and unfeeling, patiently built the infrastructure, the intricate gravitational framework that allowed the visible universe to ignite, to clump, to weave itself into the breathtaking tapestry of light and life. It is the silent, ubiquitous force, the unseen choreographer, the invisible hand that sculpted the universe from a formless void into a grand, organized spectacle. This is the profound elegance of its design, a simplicity in its nature yielding an unimaginable complexity in its outcome. It is the scaffolding of everything the silent promise fulfilled, enabling the universe to awaken to its own magnificent light. After hundreds of millions of years, shrouded in the silent, starless expanse of the cosmic dark ages, a period where the universe, though transparent, largely held its breath, the cosmos finally began its majestic awakening. It was a dawn heralded not by the sun, we know, but by the very first incandescent lights, the universe's primordial lighthouses. Around 400 million years post-Big Bang, the patient, inexorable gravitational work of the dark matter scaffolds bore profound fruit. Those subtle density enhancements, those infinitesimal wrinkles in the fabric of spacetime, had over eons attracted vast quantities of the universe's foundational elements, hydrogen and helium. Within the densest knots of this accumulating gas and invisible dark matter, a transformation began. Hydrogen and helium atoms drawn closer and closer together by the immense crushing force of gravity within these protostellar cores saw their internal pressure and temperature rise inexorably. This wasn't a gentle warming. It was a furious compression squeezing atoms into tighter and tighter spaces, increasing their kinetic energy, making them collide with ever greater force. The immense gravitational forces at play heated these burgeoning stellar nurseries to the staggering temperatures and pressures sufficient for nuclear fusion to ignite a process mirroring the very event that forged these elements in the Big Bang's first minutes. This pivotal moment marked the birth of the first star's celestial titans, known to cosmologists as Population 3 stars. These were primordial behemoths, forged solely from the universe's initial pristine cocktail of hydrogen and helium. Crucially, at this point, the heavier elements, what astronomers colloquially call metals, meaning anything heavier than helium, such as carbon, oxygen, or iron, had not yet been created. The universe's chemical palette was still remarkably simple, limited to the products of Big Bang nucleosynthesis. Their ignition was more than just a localized event. It heralded nothing less than the cosmic dawn, a transformative era when the very first beacons of light pierced the long, quiet night, beginning the arduous process of illuminating the cosmos and fundamentally altering its nascent chemical composition. It was a momentous turning point in the universe's unfolding saga. These first stars, burning with an intensity born of their colossal size and pure composition, began the universe's grand project of complexification. They were the furnaces that would slowly, inexorably transmute the simple elements into the building blocks of everything that followed. Their radiant energy also began to affect their surroundings, ionizing the neutral gas that still permeated the vast space between these nascent stellar islands. This was the opening act of a new era, moving from the dark, cold uniformity of the earlier eons to a dynamic, luminous future. The appearance of these luminous giants, born from the gravitational embrace of the unseen dark matter, truly shattered the pervasive quiet and set the stage for the rich, vibrant universe we know. Imagine the profound quiet of the cosmic dark ages, a stillness so absolute it permeated every corner of the nascent universe. For hundreds of millions of years, an immense silent canvas stretched across the void, waiting. Then, within the densest knots of gas gravitationally gathered by the invisible hand of dark matter, a spark ignited. Not a gentle flicker, but a monstrous birth of light, a cataclysmic ignition that shattered the primordial night. This was the cosmic dawn heralded by the first stars. These were the Population 3 stars, celestial titans of staggering proportions, unlike anything we typically see in the universe today. Our own sun, a comfortable, steady beacon, a star that will shine for billions of years, pales in comparison. Picture a star not just twice or 10 times its mass, but hundreds, even 1,000 times more massive than our solar anchor. Born from the universe's pristine primordial brew, hydrogen and helium, the only elements forged in the Big Bang nucleosynthesis, These behemoths knew no other composition. There was no iron to lend rigidity, no carbon to form intricate chemistry, no oxygen to fuel respiration. These fundamental building blocks of rocky planets of water of life itself simply did not yet exist. Their immense gravitational collapse squeezed their cores to unimaginable densities and temperatures. They didn't just burn, they roared incandescent furnaces, devouring their fuel at a furious, breathtaking rate. Due to their monumental mass and the crushing internal pressures, nuclear fusion within them proceeded at breakneck speeds. Their lives were not measured in comfortable billions of years, like later stellar generations, but in frantic, spectacular bursts of mere millions. A fleeting cosmic blink, a momentary flash in the grand cosmic timeline, yet every second of their existence was an act of creation and profound transformation. As these first stars blazed their furious high-energy light, pierced the encompassing gloom of the Dark Ages. Their intense ultraviolet radiation, a formidable cosmic solvent, ripped electrons from neutral hydrogen atoms in their vicinity. This process, akin to a colossal cosmic scrubbing, carved out vast expanding bubbles of ionized hydrogen within the otherwise opaque cosmos. These were the universe's first oases of clarity, the very first glimpses into what would eventually become a transparent, light-filled universe. The long night was slowly, meticulously giving way to day. But their greatest legacy, their most profound impact, lay not in their spectacular lives, but in their even more spectacular deaths. These primordial giants were destined for a swift, fiery end. Unlike stars of later generations, which could form from gas enriched with heavier elements and might gently fade into white dwarfs or collapse into neutron stars. These pure behemoths, lacking the stabilizing influence of heavier elements in their cores, lived on the very edge of existence. Many, perhaps most likely, collapsed directly into incredibly massive black holes, adding to the universe's unseen gravitational architecture, forever shaping the dynamics of emerging galaxies. Yet the most massive among them, those exceeding a certain critical threshold, met their demise in cataclysmic explosions, hypernovae events, so powerful they dwarf the supernova we witness today. These stellar funerals were the universe's first true acts of chemical alchemy. For within their incandescent cores, in the crucibles of fusion forged by unimaginable pressure and heat, these first stars had labored tirelessly. They had created the very first heavy elements: carbon, oxygen, nitrogen, silicon, iron. The fundamental ingredients for rocky planets, for the molecules of water, for the intricate chemistry of life. These precious elements scattered across the nascent cosmos by the stupendous force of their explosions were the cosmic dust, the fertile seeds for the next generation of stars, the first generation to be born of enriched stellar material. The universe, through these ephemeral, short-lived giants, was seeding its own future, irrevocably shifting from an era of cosmic simplicity and pervasive darkness to one of astonishing chemical complexity and emergent light. Their short, furious lives were a necessary sacrifice, igniting the path towards a star-studded, element-rich cosmos. The grand design woven into the very fabric of space-time since the first moments of the Big Bang was slowly, inexorably unfolding, driven by these first magnificent cosmic behemoths. The fiery, brief lives of the population 3 stars, those colossal primordial behemoths that ignited the cosmic dawn, culminated in explosions of unimaginable power, the universe's very first supernovae. These were not the controlled, elegant deaths of stars we often observe in the present-day cosmos. Lacking the heavier elements, the metals as astronomers define any element heavier than helium, which play a crucial role in regulating the fusion processes and internal structure of later stellar generations. These first stars burned through their hydrogen and helium fuel with furious speed and raw intensity. When their nuclear furnaces exhausted their primary fuel, their immense gravitational cores collapsed with terrifying speed, then rebounded in titanic blasts that ripped apart the very fabric of space-time around them. These were no ordinary stellar deaths. These were cataclysms on a cosmic scale, a fundamental act of cosmic alchemy. The sheer energy released in these core collapse supernova was immense, scattering the newly forged elements into the pristine, largely unpolluted interstellar medium. Carbon, oxygen, nitrogen, iron, silicon, and indeed all the other elements essential for the subsequent formation of rocky planets, for the intricate dance of complex chemistry, and ultimately for the emergence of life itself, were not created in the Big Bang. They were forged in the crucibles of these first stars' cores, synthesized through stellar nucleosynthesis during their brief incandescent lives, and then violently expelled across vast distances by the sheer force of these explosions. Before these supernovae, the universe was a simple place chemically. Its palette was limited to the stark purity of hydrogen-helium and a trace of lithium products of Big Bang nucleosynthesis. Afterwards, everything changed. The cosmos was enriched, infused with a newfound chemical diversity, now capable of supporting a far greater array of phenomena. The death of these first stars was paradoxically the birth of the chemical complexity that now defines our universe. It made possible the very building blocks of biological systems, from the carbon that forms the backbone of organic molecules to the oxygen we breathe, the iron in our blood, and the silicon in the rocks beneath our feet. Every atom heavier than helium in your body, in our planet, in every star and galaxy beyond the first generation, is a direct legacy of these ancient, short-lived titans. They lived, they burned, they died, and in doing so, they provided the raw material for everything that followed. This dramatic narrative of stellar birth and death, a cosmic cycle of creation and destruction, is fundamental to the universe's evolution. It explains how a cosmos born from simple elements transformed itself into a rich, complex chemical environment, fertile ground for the formation of subsequent generations of stars and the intricate planetary systems that would host them. The first metals scattered across the cosmic canvas, forever altering its destiny. Imagine for a moment standing at the very edge of sight, peering into an infinite, featureless expanse. For hundreds of millions of years, this was the universe, a vast, cold ocean of neutral hydrogen and helium gas, a profound and pervasive darkness that swallowed light whole. It was like a world perpetually shrouded in an impenetrable mist, where no ray of sunshine could ever truly break through a silent realm, echoing the quietude of the cosmic dark ages. The universe had been transparent once before, briefly after the cosmic veil lifted. But then the light had streamed away, leaving behind a new kind of darkness. Not opaque chaos, but a suffocating uniformity of neutral gas. This was a realm where photons, if they were even born, would be swiftly absorbed. Their journey cut tragically short by the omnipresent, uncharged hydrogen atoms poised to capture every energetic whisper of light. But then came the cosmic dawn, whispered into being by the colossal, short-lived titans of population 3 stars, the universe's first beacons born of pure hydrogen and helium, burning with an almost unimaginable intensity. Their fierce lives and their spectacular explosive deaths, as supernova began to inject a new, overwhelming force into the cosmic tapestry, a torrent of powerful, high-energy ultraviolet radiation. These weren't just pinpricks of light. They were cosmic flamethrowers, each photon, a miniature bullet of pure energy aimed at the heart of the universe's deep, pervasive fog. Remember the universe's thick, opaque plasma phase before recombination, before the cosmic veil. That was a universe where electrons and protons danced freely, constantly scattering light. Now, in the Dark Ages, the electrons were bound to the protons, forming neutral hydrogen atoms. And it was these neutral atoms that formed the new, more subtle but equally pervasive barrier. Its single electron, tightly bound to its proton, was perfectly poised to absorb any energetic photon that tried to pass. This was the cosmic fog, absorbing light across certain wavelengths, keeping vast swathes of the cosmos veiled, rendering it impenetrable to our sight, even if we had been there. But the first stars, these celestial furnaces, pumped out prodigious amounts of ultraviolet light. These photons were so energetic, so potent, that they carried enough punch to rip that electron away from the hydrogen atom, entirely liberating it once more. This process is called reionization, turning neutral gas back into a plasma. It was the universe unbinding itself again, but this time selectively with surgical precision. Imagine this. You're in a vast, foggy hall. Initially, your small flashlight beam just scatters and fades. But now imagine 1,000, 1,000,000, 1,000,000,000 flashlights, each one exponentially more powerful than yours, all turning on simultaneously within the fog. What happens? They don't just scatter the light. They begin to burn away the fog, creating tunnels of clarity. Around each nascent galaxy, around each cluster of these titanic early stars, a bubble of ionized hydrogen began to form. These bubbles were transparent to light, growing steadily, pushing back against the neutral, opaque medium surrounding them. It was a universe of expanding clearings like ice melting in a vast, cold ocean. And it wasn't just the stars. As the first massive clumps of dark matter coalesced and pulled in vast reservoirs of gas, some of this gas would fall into the nascent supermassive black holes at the centers of these proto-galaxies. These active galactic nuclei, known as quasars, became luminous beacons of unimaginable power. Picture cosmic lighthouses, their brilliant jets, and accretion disks pouring out even more intense high-energy radiation, accelerating the process of reionization. These were not just sources of light. They were engines of cosmic transformation, carving out vast superheated caverns of ionized gas, further eroding the veil. For hundreds of millions of years, from approximately 400 million years after the Big Bang until roughly 1 billion years after this grand cosmic drama played out. The individual bubbles of ionized gas expanded, merging with their neighbors, coalescing into ever larger regions. It was a slow, inexorable clearing, a universal unwrapping of the cosmic gift, a gradual triumph of light over the lingering shadow. The universe became a patchwork quilt of transparency and opacity, with the clear patches growing larger and larger until they touched and merged. By about 800 million to 1 billion years post-Big Bang, the universe had largely completed its profound transformation. The pervasive neutral hydrogen, once the universe's veil, had been almost entirely reionized, becoming transparent once more. Light finally could travel unimpeded across vast cosmic distances, stretching across billions of light years, carrying with it the tales of newly formed galaxies and the nascent cosmic web. This was the universe's second and final great unveiling, a universe that had learned to let light shine through. This epoch of Reionization was more than just a chemical change. It was the universe truly awakening from its long, quiet slumber. It allowed the structures we now see, the faint echoes of the seeds of structure, to finally reveal themselves. Without this cosmic clearing, without the intense pioneering radiance of the first stars and quasars, the universe would still be shrouded a mystery impenetrable to our most powerful telescopes. Our ability to peer into the distant past to witness the universe in its energetic youth. To read the story written in the light of the earliest galaxies is a direct legacy of this dramatic era, the Reionization unveiling. It marks the moment when the cosmic curtain finally lifted, revealing the grand drama unfolding within. With the great veil lifted, with the universe now transparent and infused with the first precious metals forged in the crucibles of colossal stars, a profound question hung in the vast silence. What comes next? How does a diffuse, largely featureless expanse, however enriched, coalesce into the dazzling cities of stars we observe today? The answer lies in the persistent, patient hand of gravity, working in concert with the invisible scaffold of dark matter to begin constructing the universe's very first cosmic cities, the proto-galaxies. Imagine, if you can, a cosmos still in its tumultuous adolescence. Not the grand, elegant spirals or the majestic ellipticals that grace our modern celestial atlas, but something far more raw, more chaotic, yet pregnant with promise. These were the universe's earliest attempts at large-scale structure, the foundational building blocks that would eventually birth the galaxies we know. They were irregular, clumpy assemblages, vast reservoirs of neutral hydrogen and helium gas, now seasoned with the life-giving dust of carbon, oxygen, and iron, all nestled within the pervasive, invisible embrace of dark matter halos. Consider the immense gravitational wells created by these dark matter concentrations, the very structures that gravity had painstakingly sculpted during the cosmic dark ages. These invisible anchors relentlessly pulled in the surrounding gas, which, having been enriched by the supernovae of the population 3 stars, now possessed the critical ingredients for a new generation of stellar birth. As the gas accumulated within these burgeoning dark matter cocoons, its density and pressure rose. The universe, having patiently waited for hundreds of millions of years, was now primed for an explosion of light on an unprecedented scale. This was a period of intense, almost frenzied activity. Within these proto-galactic clumps, stars began to ignite not in measured paces, but in furious, explosive bursts. The enriched gas, collapsing rapidly under gravity's unrelenting pull, sparked widespread star formation, transforming vast clouds of hydrogen and helium into dazzling nurseries of hot, massive, and very bright stars. These were the universe's first population 2 stars, inheriting a cosmos already far more complex than the one their primordial ancestors knew. Their light, piercing through the newly Reionized medium, further illuminated the burgeoning cosmic tapestry. These proto-galaxies were not static entities. They were dynamic, hungry beasts, constantly pulling in more gas from the surrounding intergalactic medium and crucially merging with smaller clumps of stars and other nascent galaxies. Picture a cosmic dance, slow and inexorable, where smaller islands of light are drawn together, colliding and coalescing their gravitational embrace, leading to even larger, more complex structures. This relentless process of accretion and merger was the primary engine of galactic growth in the early universe, shaping these irregular, chaotic forms into something larger, denser, and more gravitationally dominant. It was the universe finding its form, a process of self-assembly on the grandest scale. From the delicate, almost imperceptible quantum fluctuations of the earliest moments, amplified by inflation and sculpted by dark matter, now emerged the very first visible signs of cosmic architecture. These were the true building blocks, the cosmic Legos that over billions of years, through countless mergers, gravitational interactions, and cycles of star birth and death, would evolve into the magnificent spirals, grand ellipticals, and diverse irregular galaxies that populate the cosmic web stretching across the observable universe. The cosmos had awakened not with a whisper, but with the roar of a billion newly born stars laying the foundation for everything that would follow. As billions of years elapsed, gravity continued its patient, inexorable work on cosmic scales, sculpting the universe into a breathtaking, intricate tapestry known as the cosmic web. This vast structure is not uniform. It's a colossal network of galaxy clusters and superclusters strung along immense filaments of dark matter and gas punctuated by gargantuan, nearly empty regions called voids. Imagine a cosmic spiderweb, where galaxies are like dewdrops clinging to the invisible silk threads. These filaments, stretching for hundreds of millions of light-years, are the densest regions where gravity has had the longest time to pull matter together. At the intersections of these filaments lie the superclusters, the largest known structures in the universe, colossal aggregations of thousands of galaxies. The voids, conversely, are the vast underdense regions millions of light-years across, where matter is scarce. This foam-like, sponge-like structure is the result of the gravitational amplification of those initial tiny quantum fluctuations, a testament to the universe's self-organizing power on the grandest scales. The Cold War cast its shadow not only over nations, but subtly over our cosmic understanding. In an era fraught with geopolitical tension, two titans of cosmology from opposing sides of the Iron Curtain engaged in a different kind of ideological struggle, a profound debate over the universe's fundamental architecture. It was a contest of ideas, a clash of visions playfully yet accurately termed the meatballs versus pancakes debate. Imagine the quiet, contemplative figure of James Peebles, a Canadian astrophysicist, his gaze upon the cosmic canvas. Peebles championed what would become known as the bottom-up model of structure formation. His vision was one where the universe, initially almost perfectly smooth, began to coalesce into small, discrete lumps. Think of tiny gravitational seeds scattered across the immense cosmic void, slowly but inexorably pulling in matter around them. These modest clumps of dark matter and gas would eventually form the first galaxies, the humble building blocks. Over billions of years, driven by the relentless, patient hand of gravity, these galaxies would then gently merge and accrete, drawing more and more matter into their growing embrace. This process, Peebles posited, would lead to a universe where the largest structures, the galaxy clusters, would resemble somewhat spherical, isolated meatballs, dense, self-contained aggregations of stellar cities, each a testament to countless mergers. It was a gradual hierarchical assembly where the small paved the way for the large, a cosmic construction project building from the ground up. Its beauty lay in its simplicity and adherence to gravitational instability on local scales, allowing structures to grow step by step like droplets coalescing. Across the divide in the Soviet Union stood Yakov Zeldovich, a grizzled veteran of the Soviet atomic program. His approach to the universe was honed in the crucible of state-driven scientific endeavors, almost engineering-like in its pragmatism. His was the top-down model, a stark contrast to Peebles's vision. Zeldovich envisioned a universe where the initial tiny quantum fluctuations, those infinitesimal ripples in the fabric of space-time, would not just grow into small lumps, but preferentially collapse into immense flattened sheets or pancakes of matter on cosmic scales. These colossal structures, stretching for hundreds of millions of light-years, would form first like immense two-dimensional walls of matter. Within these pancakes, as the density continued to increase, the matter would then fragment, collapsing further under its own gravity to form smaller, denser objects, the galaxies and galaxy clusters. This model implied a universe with a more interconnected web-like structure, where the pancakes were the primary gravitational attractors dictating the overall cosmic architecture before giving birth to individual galaxies. Zeldovich's elegant mathematical framework suggested gravity's dominant effects on the largest scales would naturally lead to these sheet-like collapses, a direct consequence of initial perturbations. This intellectual clash was more than theoretical musing. It reflected fundamental differing approaches to understanding early gravitational collapse. With limited observational data, both models offered compelling divergent narratives for the universe's unfolding. Was the cosmos a tapestry woven from countless individual threads slowly intertwined? Or was it a grand, preordained stencil etched in the earliest moments that then broke apart into its constituent pieces? As decades unfolded and new cosmic insights flowed from observatories, the universe itself became the ultimate arbiter. Surveys mapping the distribution of galaxies across vast swathes of space, combined with increasingly precise measurements of the cosmic microwave background's anisotropies, began to paint a nuanced picture. What emerged was a cosmic web, a breathtaking network of filaments and sheets punctuated by massive clusters and vast empty voids. The reality, as often happens in scientific discovery, proved a magnificent synthesis, a subtle blend that defied either-or. While the hierarchical bottom-up formation championed by Peebles proved largely correct for the genesis of individual galaxies and their gradual merging into clusters, the large-scale morphology of the universe, its foam-like, sponge-like structure, with its immense filaments and walls, certainly resonated with aspects of Zeldovich's pancake predictions. The initial density fluctuations, while giving rise to smaller structures, could indeed, on the grandest scales, collapse anisotropically into the sheet-like and filamentary patterns we observe. The meatballs versus pancakes debate born from Cold War intellectual ferment stands as a testament to the dynamic, often contested nature of scientific progress. It underscores how brilliant minds driven by an insatiable hunger to comprehend the universe can arrive at profound, albeit initially opposing, truths. The universe in its boundless complexity whispers its secrets not as a singular voice, but a symphony of competing theories, each adding a vital note to the grand cosmic composition. It reminds us that understanding the cosmos is less about finding a single answer and more about embracing the multifaceted elegance of its unfolding mysteries, an ongoing saga that continues to shape our place within the infinite. The grand stage of the cosmos had long been set by the silent void, the Big Bang's shattering genesis, and the whispers of inflation. Life itself, as we understand it, hinges on the very architecture of the universe, on how matter coalesced into stars and galaxies. And for decades, the very blueprint of that architecture was fiercely debated in the hallowed halls of cosmology, a clash of titans of intellects, as vast as the universe itself, the meatballs versus pancakes debate. We've seen how Jim Peebles, with his elegant, bottom-up vision, envisioned small clumps forming, first coalescing into larger spherical galactic clusters, like cosmic meatballs. Then there was Yakov Zeldovich, the Soviet physicist, who championed a top-down approach, predicting that vast sheet-like structures, cosmic pancakes, would collapse first, fragmenting into galaxies. Each model, compelling in its own right, offered a distinct path to the cosmic web we observe. For a time, it seemed an either-or proposition, a binary choice in the grand narrative of creation. But science, in its truest form, rarely offers such stark simplicity. The universe, in its boundless ingenuity, often chooses a path far more complex, far more elegant, synthesizing seemingly disparate truths into a richer, unified understanding. It was into this intellectual crucible that Richard Gott, a brilliant mind with a knack for visualizing the unseen, stepped forward. He understood that the universe's structure wasn't a matter of one model unequivocally triumphing over the other. The very fabric of reality, the cosmic web, was a testament not to a singular process, but to a grand interplay. Gott, observing the burgeoning data from early galaxy surveys and the increasingly sophisticated computer simulations, that were beginning to map the universe's large-scale structure, proposed a compelling intuitive solution. The universe on its grandest scales resembled a cosmic sponge. Imagine not merely isolated clusters floating like meatballs in space, nor just flat sheets of galaxies stretching endlessly. Instead, envision a three-dimensional network, intricate and interconnected, like the porous structure of a natural sponge. This sponge topology, as Gott famously articulated, beautifully reconciled the apparent contradictions of the meatballs and pancakes models. It suggested that both types of structures existed not as mutually exclusive phenomena, but as complementary features within a single grand design. The walls, or filaments, of the sponge represented the denser regions of the cosmic web, the pancakes of Zeldovich's vision. These were the long, sinuous threads of matter stretching for hundreds of millions of light-years, along which galaxies and clusters were strung like pearls on an invisible necklace. These were the regions where gravity had diligently pulled in gas and dark matter over eons, creating the densest aggregations. And at the intersections of these filaments, where multiple walls converged, lay the superclusters, the truly colossal, meatball-like knots, the universe's most massive cities of galaxies. But just as crucial to the sponge's structure were the holes, the vast, nearly empty regions known as voids. These immense caverns, millions of light-years across, were the antithesis of the filaments regions where matter was sparse, where gravity's tug was weakest. In Gott's model, these voids were not merely empty spaces between clusters. They were interconnected, forming their own vast network, flowing into one another, much like the interconnected pores of a sponge. They were the universe's negative space, equally defining its structure as the matter that outlined them. This elegant synthesis revealed that both bottom-up accretion, the slow gravitational accumulation of smaller clumps into larger structures, and top-down collapse, the initial formation of large sheet-like distributions that then fragmented, were integral to the universe's evolution. The tiny ripples, the quantum fluctuations from the inflationary epoch, amplified by the pervasive invisible scaffold of dark matter, had over billions of years orchestrated this intricate dance. Dark matter, collisionless and cold, had formed the initial gravitational wells, drawing in ordinary baryonic matter, shaping the proto-filaments and proto-voids. As the universe expanded and cooled, these slight density variations solidified into the majestic sponge-like web we see today, a testament to gravity's patient artistry on the grandest scales. The cosmic web, in its sponge-like glory, is not just a scientific model. It is a profound realization of the universe's self-organizing power. It underscores that the universe's beauty lies not in a singular, simplistic pattern, but in the astounding complexity that emerges from fundamental forces. The resolution of the meatballs versus pancakes debate into Gott's sponge was more than just a scientific victory. It was a revelation showing that the cosmos, like our understanding of it, is a continually evolving tapestry, infinitely more fascinating than any single theory could capture. It leaves us with an enduring sense of awe, standing at the precipice of infinity, gazing upon the universe's colossal, intricate blueprint, ever more aware of the astonishing artistry hidden within the depths of time and space. In the breathtaking vastness of the cosmic web, that intricate tapestry of galaxies, filaments, and voids, we have begun to explore a fundamental question emerges for each of us. Where exactly do we reside within this immense unfolding grandeur? To truly comprehend our place in this cosmic drama, we must undertake a mental journey, zooming out from our familiar terrestrial address to our sprawling cosmic one, a profound exercise in perspective. Our journey begins, of course, on Earth, this pale blue dot. We orbit our sun, a single star, one of hundreds of billions swirling within the grand spiral of the Milky Way galaxy. The Milky Way, with its majestic arms and bustling central bulge, is our immediate galactic home. But our galaxy, magnificent as it is not alone in the vast cosmic ocean. It is part of a relatively small collection of about 50 galaxies gravitationally bound together, known to astronomers as the local group. This cosmic neighborhood is dominated by our own Milky Way and its colossal counterpart, the Andromeda Galaxy. Andromeda, a majestic spiral itself, is currently on a collision course, with us a monster encounter set for billions of years in the future, promising a spectacular if slow-motion merger that will reshape our galactic future. The local group, in turn, is merely a tiny speck on the outskirts of an even larger structure, the Virgo supercluster. This supercluster, named for its dominant central cluster in the constellation. Virgo represents a significant concentration of galaxies, acting as a regional gravitational basin. But even the Virgo supercluster, once thought to be our ultimate cosmic address, proved to be just another step on the ladder of cosmic hierarchy. Recent groundbreaking astronomical mapping, utilizing the precise measurement of galactic movements and gravitational flows, has revealed an even grander assembly of galaxies, a truly vast gravitationally bound structure that encompasses not just the local group and the Virgo supercluster, but many more. This colossal structure, stretching across an astounding 520 million light-years, contains over 100,000 galaxies and boasts a mass equivalent to 100 million billion suns. It is known as the Laniakea supercluster. Its name, derived from the Hawaiian language, is deeply evocative, meaning immeasurable heaven. This is our cosmic address, a magnificent and humbling testament to the universe's inherent hierarchical organization, revealing that even on the largest scales, matter clumps together into structures of escalating complexity. Laniakea itself is not a static entity. Its constituent galaxies, including our own, are inexorably flowing towards a common gravitational center, a cosmic drain that hints at even greater, as yet unseen concentrations of mass. This grand cascading structure from the local to the supercluster scale is a direct consequence of the continuous patient work of gravity, steadily pulling matter towards the densest regions created by the dark matter scaffold. Understanding our cosmic address is not just about mapping coordinates. It is about grasping our infinitesimal yet interconnected place within the universe's grand unfolding story, a story that continues to reveal ever larger scales of structure, pushing the boundaries of our comprehension. It compels us to ask what lies beyond even Laniakea, our cosmic address. The Laniakea supercluster is a testament to the universe's hierarchical organization, a magnificent, sprawling metropolis of galaxies bound by the patient, relentless hand of gravity. Yet even within this immeasurable heaven, this grandest known structure, a profound mystery persisted, a subtle gravitational whisper hinting at forces and structures far grander, far more enigmatic than anything we had yet fully comprehended. Imagine for a moment that you are a cosmic cartographer diligently mapping the expansion of the universe. You expect to see galaxies moving away from each other, carried along by the stretching fabric of space-time itself, a predictable, majestic flow. But then anomalies begin to emerge, peculiar shifts in the cosmic dance. Galaxies, including our own local group, the Milky Way and Andromeda, weren't just passively participating in this grand cosmic ballet of expansion. They were also being pulled inexorably towards something else, something hidden at speeds of hundreds of kilometers per second, velocities significantly exceeding the general cosmic recession. It was as if an unseen current, a powerful silent river of gravity, was dragging our entire corner of the universe. This was no ordinary drift. These were the peculiar velocities, motions superimposed on the universe's overall expansion, pointing towards a singular, incredibly massive gravitational anomaly. For decades, astronomers employing ever more sophisticated telescopes and computational models meticulously observed these telltale signs, cosmic breadcrumbs scattered across the vastness, leading directly to an invisible source. It was a true cosmic detective story, played out on the grandest stage, where the only clues were the subtle yet undeniable altered trajectories of entire galactic populations, their silent whispers of an unseen force. The culprit, though unseen, eventually received its fitting moniker, the Great Attractor. It is a colossal diffuse concentration of mass roughly 150 million light-years away from us, an immense gravitational well that holds our local group, and by extension, the entire Laniakea supercluster in its insidious tug. Think of it not as a single compact object, but as a truly vast, sprawling region where matter, particularly the elusive dark matter, has accumulated to an unprecedented, almost unfathomable degree. Its true nature and precise composition remain one of the universe's most captivating enigmas, challenging our very understanding of cosmic distribution. Why can't we simply point our powerful telescopes at this titan of gravity, this silent architect? Because the Great Attractor lies directly behind what astronomers call the zone of avoidance. This is a region of the night sky heavily obscured by the dense dust and gas of our own Milky Way galaxy. Our galactic plane, stretching across the sky, acts like a thick cosmic fog bank, an opaque curtain blinding us to what lies beyond. Imagine standing in a dense, swirling fog on a moonless night. You can feel a relentless, powerful current tugging at you, pulling you forward, but the source of that force remains completely hidden, swallowed by the impenetrable gloom. We feel its undeniable pull, map its profound influence on cosmic flows, but its face remains utterly veiled. Like the invisible hand of dark matter that so patiently built the cosmic scaffolds upon which galaxies first formed the Great Attractor, serves as yet another profound testament to gravity's pervasive, often unseen influence. It highlights the humility of human understanding, revealing that even with all our advanced instruments, our intricate theories, and our ever-expanding cosmic maps, there are still titanic, unseen forces shaping our cosmic neighborhood, orchestrating movements on scales that defy easy comprehension. The mystery of the Great Attractor beckons us forward, a tantalizing invitation to unravel its true nature, to pierce through the cosmic veil, and to add yet another breathtaking chapter to humanity's ever-unfolding story of cosmic discovery. It reminds us that the universe is an endless source of wonder, continually surprising us with its hidden depths and its silent, powerful architects, urging us to look closer, to dream bigger. As if the mysteries of the Great Attractor, that unseen gravitational well tugging at our supercluster, weren't enough, another profound anomaly lingers within the very fabric of our earliest cosmic memories. It is a puzzle that challenges our most fundamental cosmological assumptions, a perplexing alignment so unsettling that cosmologists have given it a rather dramatic, almost ominous name, the so-called axis of evil. This provocative term, coined out of frustration and deep scientific curiosity, refers to an inexplicable and unnerving alignment detected in the cosmic microwave background, or CMB, the universe's ancient luminous baby picture, that fossil relic from 380,000 years post-Big Bang. The CMB, as we explored, is overwhelmingly uniform across the sky. This incredible homogeneity and isotropy, meaning it looks roughly the same in all directions and at all locations, is a cornerstone of the Copernican principle, which humbly states that we are not special, that our position in the universe is not a preferred one. This principle underpins much of modern cosmology, suggesting a universe that is on large scales remarkably simple and predictable. Yet within this vast uniform canvas, subtle fluctuations exist, tiny temperature differences of mere parts per million, which are the gravitational seeds of all future cosmic structure. However, it is the largest of these fluctuations, specifically components known as the quadrupole and octupole moments of the CMB, that present the most profound and persistent puzzle. These grand sweeping patterns across the sky appear against all theoretical expectations to be subtly aligned with our very own solar system's ecliptic plane, the orbital plane of the planets around the Sun. Even more unsettlingly, some analyses suggest an alignment with the direction of our own galaxy's motion through space. This is deeply puzzling because in a truly isotropic and homogeneous universe, there should be no such preferred directions or correlations with local structures. The universe's largest, most ancient patterns should not care about the orientation of our tiny solar system or our galaxy's peculiar velocity. Such a correlation hints at a possible breakdown of the cosmological principle on the very largest scales, forcing physicists to consider radical, uncomfortable possibilities. Does it imply that the universe isn't as isotropic as we believe, that there is some subtle underlying directionality imprinted from its earliest moments? Or does it point to a previously unknown cosmological effect, a new piece of physics that our current models simply cannot account for? It is a mystery that threatens to shake our understanding of the universe's fundamental architecture, forcing us to confront the possibility that perhaps, just perhaps, our cosmic address holds an unexpected and unsettling significance, contradicting the very notion of our cosmic insignificance. The axis of evil remains one of the great open questions in cosmology, a tantalizing cosmic anomaly that reminds us of the profound unknowns still hidden within the deepest reaches of space-time, forever challenging our assumptions about the universe's true nature. For billions of years, a profound cosmic expectation hung heavy in the void. After the cataclysmic roar of creation, after the universe had expanded and cooled from its unimaginable inferno, an undeniable truth seemed to govern its ultimate destiny: gravity. It was the patient, relentless architect, constantly pulling, constantly shaping, striving always for unification and collapse. Cosmologists, those intrepid cartographers of the cosmos, peering into the deep past with their advanced instruments, observed a universe where the very fabric of space-time was locked in a deceleration dance, a gradual, stately slowing of its outward rush. Imagine, if you will, the most powerful cannon in existence, firing a colossal projectile straight up from the surface of an impossibly massive planet. Initially, the projectile rockets skyward, defying the crushing gravitational pull with sheer momentum. But with every passing second, the planet's immense gravitational field tugs back, subtly, inexorably robbing the projectile of its velocity, slowing its ascent. There is an unspoken battle, a constant struggle between the initial explosive energy and the pervasive, attractive force of mass. The universe in its furious aftermath was akin to that projectile. For roughly the first 5 billion years of its existence, a colossal span of time by human standards, the outward rush, the very expansion of space itself, was continuously fighting against an unseen, omnipresent drag. This drag was not a theoretical construct. It was the tangible collective gravitational pull of everything within the cosmos. Every swirling galaxy, a city of 100 billion stars. Every colossal cluster of galaxies, holding thousands of these star cities in its embrace. Every intricate filament of the cosmic web, stretching across unimaginable distances. Every phantom halo of dark matter, the invisible scaffold, the silent architect that underpins all visible structure. All of these components, vast and disparate, exerted a mutual inexorable attraction on one another. This immense cumulative gravity acted as a cosmic brake, steadily reining in the explosive outward momentum imparted by the Big Bang. The universe was by all accounts decelerating. Its expansion rate, though still incredibly swift, was slowing down over vast stretches of cosmic history, like a runner growing weary in a race against an invisible force. How did humanity, mere inhabitants of a small blue planet, perceive this subtle universe-wide breaking through the painstaking study of cosmic beacons, distant supernovae? These cataclysmic stellar explosions, particularly a specific type known as type Ia supernovae, are remarkable celestial phenomena. They occur when a white dwarf star, the super-dense remnant of a star like our Sun, accretes enough matter from a companion star to reach a critical mass, triggering a runaway thermonuclear explosion. Crucially, these explosions are incredibly uniform in their intrinsic brightness. They are, in essence, the universe's most reliable, standard candles, cosmic light bulbs of known luminosity. By meticulously observing how dim these supernovae appeared from Earth, astronomers could precisely calculate their distance across the vast, expanding cosmos. And by simultaneously measuring the redshift of their light, the stretching of light waves as the universe expands, they could determine how fast the space between us and them had expanded since that ancient light began its millions or billions of years-long journey. For decades, the data meticulously collected from these cosmic lighthouses seemed to confirm the prevailing cosmological wisdom the universe was indeed slowing down. The expectation deeply ingrained in the scientific community was clear and seemingly inescapable. If gravity continued its relentless, pervasive work, the cosmos might eventually reach a peak expansion, a maximum size, and then perhaps even begin to reverse course, contracting inward, compressing everything back into an unimaginable density in a grand, fiery Big Crunch. It was a coherent, elegant narrative, a predictable cosmic fate seemingly dictated by the very laws of physics. But the cosmos, that boundless realm of wonder and unexpected truth, ever the purveyor of grand surprises, had a profound, paradigm-shattering twist in store for humanity, a revelation that would forever redefine our understanding of its ultimate fate, forcing us to confront a cosmic reality far stranger than our most compelling theories. For billions of years, the universe had played out a cosmic drama with a seemingly predictable plot twist. We had thrown the ball, and for 5 billion years, gravity had been pulling it back steadily, inexorably. The grand cosmic expansion, the initial furious rush from the Big Bang, was supposed to be slowing down, decelerating under the immense collective weight of all matter and energy within the cosmos. This was the elegant expectation, the logical conclusion derived from all we understood about the universe's mass and the persistent tug of its fundamental forces. The cosmic recoil, a gentle breaking, was the accepted narrative, a testament to the universe's internal gravitational accounting. Scientists, the meticulous auditors of the cosmos, peered into the deep, ancient light of distant supernovae, seeking to precisely measure this expected slowdown to quantify the universe's inevitable deceleration, perhaps even to predict a future Big Crunch, umberfoin onsestum. What they found, however, was not a slowdown, but a startling acceleration, a profound reversal of cosmic fortune that would rewrite the very laws of the universe's destiny. It was the year 1998, a watershed moment in the annals of astrophysics. Two independent teams, one led by American astronomer Saul Perlmutter, the other jointly by American Adam Rees and Australian Brian Schmidt, were meticulously analyzing the light from type Ia supernovae stellar explosions of a particular consistent brightness. These standard candles were cosmic lighthouses, their known intrinsic luminosity, allowing astronomers to calculate their exact distance. By comparing this distance with their measured redshift, the stretching of their light due to the universe's expansion, scientists could gauge how fast the cosmos was expanding at different points in its history. The teams expected to find the supernovae slightly brighter than predicted for a universe slowing down. Instead, they were unexpectedly dimmer. Far dimmer. This wasn't an error in their calculations. It was a cosmic whisper turning into a roar, screaming that these distant celestial explosions were further away than they should have been in a decelerating universe. The only way this could be true was if the expansion itself had not been slowing, but had in fact begun to speed up. The implications were staggering, a scientific revelation that shattered preconceived notions and ushered in a new era of cosmic mystery. To explain this unprecedented acceleration, a new, entirely enigmatic force had to be invoked, a repulsive pressure permeating the very fabric of space-time itself. We call it dark energy. It is the single largest component of our cosmos, an invisible, intangible entity comprising approximately 68% of the universe's total mass energy budget. Ordinary matter, the stuff of stars, planets, and us, makes up a mere 5%. Even dark matter, the invisible architect we previously encountered, accounts for only 27%. Dark energy dwarfs them all, yet its nature remains one of the deepest, most perplexing puzzles in physics, a simplicity versus complexity paradox, writ large on the canvas of the cosmos. How could something so prevalent be so utterly unknown? Is dark energy a constant energy density inherent to space-time itself, precisely as Albert Einstein's once dismissed cosmological constant might suggest he introduced this term into his equations of general relativity to achieve a static universe, a concept he later famously called his biggest blunder after Edwin Hubble's discovery of expansion. Yet a century later, Einstein's blunder re-emerged as a compelling candidate, a fundamental property of space that could provide a constant outward push. Or is it something more dynamic, a fluctuating field known as quintessence, that changes over time, ebbing and flowing, perhaps with implications for the universe's ultimate fate? Scientists are exploring every possibility, from modified theories of gravity that alter how space-time itself behaves on cosmic scales to exotic particle physics that might unveil new fundamental forces. What is certain is its effect. Dark energy exerts a negative pressure pushing space-time apart, actively counteracting gravity's pull. It is not merely lessening gravity's grip, it is actively accelerating the outward rush, driving the galaxies away from each other at an ever-increasing rate, ensuring their future appears ever more isolated and distant. This enigmatic force, once a theoretical footnote, now dominates the universe's current epoch, silently, powerfully dictating its ultimate destiny. The discovery of dark energy was a profound moment of scientific humility, reminding us that even with our most advanced instruments and profound theories, the cosmos holds secrets that dwarf our current understanding. It is a cosmic twist, a sudden acceleration in the grand narrative of existence, beckoning us to continue our tireless quest to unravel the true nature of this invisible hand, shaping the universe's relentless expansion. The universe, in its boundless mystery, continues to surprise, challenging our assumptions and forever expanding the horizons of human knowledge. The stunning cosmic surprise, the one that forced cosmologists to fundamentally re-evaluate their understanding of the universe's ultimate fate, arrived around 1998. When observations of distant Type Ia supernovae, those precise standard candles we use to gauge cosmic distances, were meticulously analyzed by rival teams led by astronomers such as Saul Perlmutter, Adam Rees, and Brian Schmidt. They yielded an utterly astonishing result. Far from showing continued deceleration, as the gravitational pull of all matter and radiation should have dictated the universe's expansion, was actually accelerating. This revolutionary discovery pointed to the existence of an entirely new, enigmatic force, a repulsive pressure permeating the very fabric of space-time dark energy. Comprising an astounding approximately 68% of the universe's total mass energy budget, dark energy is not just a minor component. It is the single largest and most dominant constituent of our cosmos, yet its nature remains one of the deepest and most profound mysteries in all of physics. What precisely is it? The leading candidate, a concept once dismissed by Albert Einstein as his biggest blunder when he introduced it into his equations, is the cosmological constant. This hypothesis suggests that dark energy is a constant energy density, inherent to space-time itself, a property of empty space, an intrinsic cosmic pressure that causes space to expand. Alternatively, some theories propose it could be a dynamic fluctuating field, a form of quintessence that changes over time, its influence waxing and waning over cosmic epochs. Scientists are actively exploring every possibility from exotic particle physics to subtle modifications of Einstein's theory of gravity on the largest scales. Regardless of its precise identity, the observed effect of dark energy is clear and profound. It exerts a negative pressure pushing space-time apart. It acts as a cosmic anti-gravity, directly counteracting gravity's attractive pull and driving the galaxies away from each other at an ever-increasing rate. This means that galaxies are not just moving away from each other due to the initial inertia of the Big Bang. They are accelerating, receding at an ever-increasing speed. The relationship between a galaxy's distance and its recession velocity, beautifully codified by Hubble's law, now includes this acceleration, revealing a universe that is not simply expanding, but actively being stretched apart by an unknown force. Redshift, the stretching of light waves from receding objects, quantifies this relentless cosmic flight. Dark energy is the dominant force in the universe's current epoch, silently powerfully dictating its ultimate destiny. Its influence has only become apparent in the last 5 billion years as the universe became sufficiently diffuse for its constant energy density to overcome the diluting effects of matter and radiation. It is this pervasive, invisible pressure that is driving the universe towards a potentially lonely and desolate future, a profound twist in the cosmic tale that continues to challenge our most fundamental assumptions about the cosmos. Imagine a sky countless eons from now. Not the vibrant starlit canvas we know, but a profound inky blackness broken only by the dim cooling embers of the last dying red dwarfs. Gone are the spiraling arms of majestic galaxies, the fiery nurseries of nascent suns, the shimmering nebulae where cosmic dust danced in the light of creation. What remains is a void, vaster, colder, and more complete than any conceived before the Big Bang itself. This chilling vision, this cosmic curtain call, is the future's shadow cast by the very force that now dominates our universe, dark energy. For approximately 5 billion years, gravity, the patient architect, held sway, slowly decelerating the universe's expansion, as Chapter 23 recounted. But then, as Chapter 24 revealed, dark energy, that enigmatic unseen force comprising nearly 68% of the cosmos, took hold. Its negative pressure, its relentless push against the very fabric of space-time, ushered in an era of accelerating expansion, sending galaxies racing away from each other at ever-increasing speeds as we explored in Chapter 25. This accelerating cosmos, a profound departure from all expectations, now dictates the universe's ultimate epic act, and cosmologists envision several possible scenarios, each more profound than the last. The most widely accepted and perhaps the most desolate future is the Big Freeze, or heat death. If dark energy remains a constant energy density akin to Einstein's resurrected cosmological constant, its influence will continue to stretch space-time apart inexorably. The cosmic dance of galaxies will gradually cease as they recede beyond each other's cosmic horizons, eventually becoming utterly invisible, their light stretched into oblivion by the accelerating expansion. Our cosmic address, the Laniakea supercluster, and even our local group will become an isolated island in an ever-expanding silent sea. The stars, those luminous crucibles that forged the first metals from the legacy of Population 3, stars will one by one burn through their nuclear fuel, shrinking into white dwarfs, neutron stars, or collapsing into black holes. The universe, once a vibrant tapestry of light and life, will slowly dim. Even the most resilient celestial remnants, the black holes, those cosmic behemoths formed from stellar collapse and galactic mergers, will eventually evaporate over truly gargantuan timescales, emitting faint Hawking radiation until nothing but a whisper of energy remains. The universe will approach a state of maximum entropy, a uniform cold, dark, and utterly empty expanse, where no usable energy exists and no processes can occur. The symphony of existence, which began with the silence of Chapter 1, will end in the profound, ineffable quiet of absolute zero. But what if dark energy, the invisible architect, were not so constant? What if its density were to increase over time, becoming even more potent? This terrifying possibility leads to a far more dramatic and violent scenario: the Big Rip. In this chilling prospect, the accelerating expansion, amplified by an ever-strengthening dark energy, would become so powerful that it would overcome all other fundamental forces. First, it would rip apart galaxy clusters, then individual galaxies, tearing apart the very gravitational scaffolds that dark matter so patiently built, as discussed in Chapter 11. Stars no longer bound by gravity would be stripped from their systems. Then planets would be torn from their stars. Eventually, the very atoms themselves, the hydrogen and helium forged in the primordial forge of Chapter 5, and the heavier elements created by the cataclysmic supernovae of Chapter 14, would be ripped apart, their nuclei and electrons separated. Finally, even the subatomic particles and the fabric of space-time itself would be shredded into oblivion, reducing the entire universe to a state of infinite density and infinite expansion. This scenario embodies the simplicity versus complexity paradox, a single simple property of dark energy, leading to the most complex and utterly destructive cosmic unraveling. Conversely, some theories ponder a reversal of dark energy's influence, or a point where gravity might somehow regain dominance. This could hypothetically lead to a Big Crunch, a return to the universe's fiery infancy, where the expansion would halt, reverse, and all matter and energy would collapse back into an infinitely dense singularity, echoing the moment of becoming in Chapter 2. Such a reversal would represent a profound cosmic recoil, a reenactment of the deceleration period described in Chapter 23, but taken to its ultimate conclusion. Or a variation of this collapse, the Big Bounce, suggests that the universe might not end in a singularity, but rather pass through it, triggering a new Big Bang, a fresh unfolding of silence, and the birth of a new universe from the collapsed remnant of the old. This cyclical view offers a tantalizing echo of the universe's initial quantum fluctuations, a perpetual rebirth from the ashes of its past. The universe's fate, while still an open question at the edge of human understanding, is inextricably linked to the mysterious nature of dark energy, the silent force guiding its final epic act. Our quest to map the cosmic web and unravel the axis of evil is not just about understanding our past or our present. It is about glimpsing the distant, shadowed future of all that is. the universe continues its profound, accelerating journey, a majestic cosmic ballet whose final movements are yet to be revealed. Even with the universe's earliest light, the cosmic microwave background, our indelible baby picture, a profound cosmic mystery, persisted. For hundreds of millions of years, from approximately 380,000 years after the Big Bang until nearly 400 million years later, the cosmos had been shrouded in a silent, starless epoch, the cosmic dark ages. During this vast expanse, the tantalizing whispers of the cosmic dawn, the fiery birth of the very first stars, the population 3 behemoths, and the earliest proto-galaxies that finally pierced that long night remained largely beyond our direct sight. We knew the cosmic recipe from Big Bang nucleosynthesis. We understood the patient work of the invisible architect dark matter and the gravitational scaffold it built slowly accumulating matter. But the actual moments of genesis for structures larger than atoms, the true first light, remained an elusive secret hidden by time and cosmic dust. Light from those primordial eons, stretched and thinned by the inexorable cosmic expansion and the accelerating cosmos driven by the enigmatic dark energy, had become a faint, almost ghost-like whisper. How could humanity, a fleeting blip on a pale blue dot, hope to peer through such immense distances and temporal veils to witness the universe's true awakening? The answer lay not in brute force, but in a delicate golden eye, a profound technological leap designed precisely to capture those almost imperceptible murmurs, the James Webb Space Telescope. Launched in 2021, JWST transcended mere incremental improvement over its esteemed predecessor Hubble, which excelled in visible and ultraviolet light. Webb was a revolution, a cosmic paradigm shift, a testament to humanity's unyielding quest for knowledge and its audacious ambition to unlock the universe's deepest secrets. Its most striking feature, an enormous 6.5-meter primary mirror composed of 18 meticulously aligned hexagonal segments, shimmered with a delicate atom-thin layer of gold. Gold, a material often associated with preciousness, was chosen here for its unparalleled reflectivity and efficiency in capturing infrared light, the very essence of Webb's mission. For the light emitted by the universe's nascent structures billions of years ago has been profoundly stretched by the relentless march of cosmic expansion, a phenomenon known as cosmological redshift. What began as scorching ultraviolet and visible light from the universe's first incandescent sources, the population 3 stars, and the bustling chaotic proto-galaxies, had by the time it traversed the vast expanding void to reach us, red-shifted into the longest, coolest wavelengths of the electromagnetic spectrum infrared. This golden eye could finally see what was previously hidden. JWST's unique design and infrared optimization allow it to pierce directly through the thick cosmic veil of dust and gas that so effectively obscures visible light. This is crucial for revealing the hidden stellar nurseries where new stars ignite and condense from gas clouds, and the very birthplaces of planets taking shape within swirling protoplanetary nebulae. Processes that were foundational to the universe's self-organization and the eventual formation of our own solar system. To achieve this unparalleled sensitivity, particularly in detecting such faint, ancient infrared signals, JWST had to be placed in an extraordinary, profoundly cold location, far from the warmth and light pollution of Earth. Nearly 1.5 million kilometers away, at the second Sun-Earth Lagrange point, it perpetually orbits the Sun, shielded by a massive tennis court-sized sun shield. This allows it to maintain an incredibly cold operating temperature of below 50 Kelvin, about 223 degrees Celsius, a frigid environment that prevents the telescope itself from emitting infrared radiation that would swamp its sensitive instruments. It is truly a cold crucible of scientific precision, silently listening for the universe's first whispers, its primordial light. More than a mere observatory, JWST is our most ambitious time machine, designed not just to observe the earliest moments after the Big Bang, but to fundamentally rewrite the very first chapters of cosmic history we have previously only inferred. It will directly witness the Reionization, unveiling the final dramatic transformation of the universe from its opaque, foggy plasma state into the transparent cosmos we know today. A monumental event triggered by the overwhelming power of the first luminous sources and the behemoths and their legacy. It will map the intricate foam-like structure of the cosmic web as it unfurls, providing crucial observational data that will help us conclusively refine our understanding of the meatballs versus pancakes debate and Richard Gott's innovative sponge topology. Furthermore, by pushing the boundaries of observable space and time, peering into the universe's past with unprecedented clarity, JWST may offer new insights into the nature of dark energy, the enigmatic force driving the accelerating cosmos and dictating its ultimate destiny, and potentially shed light on whether anomalies like the axis of evil hold true cosmic significance or are mere statistical flukes. Through its unblinking golden gaze, humanity is not merely observing the cosmos. We are embarking on a profound journey of self-discovery, understanding our cosmic address not just as a location within the Laniakea supercluster and subject to the mysterious pull of the great attractor, but as conscious beings capable of unraveling the universe's deepest, most ancient secrets. The silent, boundless void that preceded creation, the moment of becoming the inflationary whisper, the forge of lightness, the cosmic veil, and the dark ages, all are now within the reach of this extraordinary instrument. The universe in its grand unfolding saga continues to unveil itself, one red-shifted photon at a time, captured by our golden eye, a beacon of curiosity reaching across billions of years to touch the very origin of everything. It beckons us silently, powerfully into the future. The air in the command center, usually a hive of quiet industry, had grown taut with a collective breath held. Dr. Eleanor Vance, her focus unwavering, leaned into the monitor, the soft, cool light of the screen reflecting in her intent gaze. Beside her, Professor Alistair Finch, a man whose career spanned decades of cosmic observation, adjusted his wire-rimmed spectacles, a nervous habit that betrayed his inner tremor of anticipation. This was it, the first full-resolution data stream from the James Webb Space Telescope, designed to peer back to the very genesis of galactic light. For generations, cosmologists had meticulously constructed models predicting the universe's nascent years. They envisioned the cosmos a mere few hundred million years after the colossal roar of the Big Bang, as a primordial wilderness, sparse, dotted with the hesitant, clumpy formations of infant galaxies, structures still awkward and immature, slowly coalescing like fragile dewdrops on an invisible cosmic web. Then the images resolved onto the display. A sharp, involuntary intake of breath from Dr. Vance cut through the silence, followed by Professor Finch's almost reverent whisper, "Good heavens." What unfurled before them transcended every carefully calibrated prediction. These were not the tentative, formless, embryonic stellar nurseries they had expected. Instead, shimmering with an impossible brilliance against the backdrop of the universe's youth, were galaxies grand, luminous, and startlingly mature. They appeared to the stunned eyes of the scientific team like ancient entities, wise beyond their chronological age, born into a bustling maturity that defied the very concept of cosmic infancy. It was an immediate, profound realization. The universe, it seemed, had been in a far greater hurry to grow up to ignite than humanity had ever dared to conceive. One particular discovery became an instant icon of this revelation, a luminous challenge to established thought, GN-Z11. Observed just 400 million years after the universe's fiery genesis, this galaxy radiated with an astonishing luminosity and possessed a staggering mass utterly perplexing in its precocious development. How could such a monumental assembly of stars, such a developed galactic structure, have possibly congealed and ignited so rapidly? It was as if the universe in its earliest youth had not merely skipped a few developmental stages, but had actively sprinted through eons of anticipated growth, leaping from a quiet cosmic nursery directly into a vibrant, bustling galactic metropolis. This singular observation, reinforced by a torrent of similar data points from JWST's unparalleled infrared vision, sent seismic waves through the very bedrock of galactic formation theory. The long-held narrative of slow, patient bottom-up accretion, where tiny structures gradually merged over billions of years to painstakingly build larger cosmic cities, now faced an urgent dramatic revision. The implications for our understanding of cosmic evolution were nothing short of revolutionary. Were the conditions in the early universe so astonishingly efficient for star formation that entire stellar populations could burst into existence with unprecedented ferocity? Perhaps the abundant, pristine supply of cold hydrogen and helium gas, the very elements forged in the first minutes of Big Bang. Nucleosynthesis, unburdened by the complexities of heavier elements, fueled a supercharged, hyper-efficient period of stellar ignition. Or did the pervasive, invisible architects of dark matter, which Chapter 11 revealed as the gravitational scaffold, exert an even more dominant and accelerated influence than previously theorized? Their massive halos, unhindered by conventional matter's interactions with light, might have compressed and funneled gas into dense cradles at an astonishing pace, providing the perfect conditions for these luminous, mature giants to emerge with such surprising speed. This was the universe's ultimate paradox, an elegant inversion of the simplicity versus complexity motif. From the simplest raw materials, a staggering complexity of structure emerged with unexpected, breathtaking haste. JWST's golden eye had confirmed that the universe was far more vibrant, dynamic, and bustling in its infancy than humanity had ever dared to imagine. It was a universe teeming with light, a sudden, brilliant tapestry woven in a mere fraction of cosmic time. These epochal discoveries weren't just adding new paragraphs to the cosmic history books. They were compelling cosmologists to dramatically rewrite the very first chapters, entirely demanding new theoretical frameworks, new intricate simulations, and a profoundly deeper understanding of how galaxies truly begin their grand, intricate dance across the immeasurable heavens. The universe, ever the master of surprise, had once again unveiled a truth more astonishing than our most imaginative fictions, illuminating not just its past, but the uncharted, exhilarating future of cosmic research. JWST's golden eye, poised at its distant Lagrange point, was designed to peel back the layers of cosmic history, revealing the universe as it was in its earliest infancy. Its gaze into the cosmic dawn, particularly through its unparalleled infrared vision, quickly illuminated another profound mystery that has puzzled astrophysicists for decades: the rapid emergence and growth of supermassive black holes. For a long time, the central puzzle had been how these cosmic leviathans, entities, millions to billions of times the mass of our Sun, could have grown so unfathomably large so quickly in the early universe. Theoretical models traditionally suggested that black holes grow by slowly accreting gas and dust from their surroundings, a gradual process that accumulates mass over billions of years. Think of a meticulous gardener adding soil to a plant pot little by little. This slow, steady accumulation would imply that the truly massive black holes should only appear much later in cosmic history, after galaxies had ample time to form, and central matter had slowly spiraled inward. But JWST's groundbreaking observations from its very first deep fields challenged these established models directly and dramatically. The telescope revealed early galaxies formed just hundreds of millions of years after the Big Bang, some as early as 400 million years post-Genesis, as we saw in the previous chapter, already harboring supermassive black holes at their very centers. Not only were these black holes present, but many of them were actively devouring surrounding matter and shining brightly as quasars' powerful cosmic beacons, signifying intense accretion activity. This swift appearance of such behemoths, so early in the universe's timeline, simply did not fit the slow, gradual growth models. It was like finding a fully grown redwood tree in a newly planted sapling forest. This profound discovery hinted at alternative formation scenarios, suggesting that the universe's infancy was far more dynamic and extreme than previously imagined. One leading hypothesis is the direct collapse scenario, where massive clouds of primordial gas, perhaps triggered by the immense gravitational potential of dark matter, halos, might have bypassed the star formation phase entirely and collapsed directly into black holes with masses hundreds of thousands of times that of the Sun. Another possibility involves a process of rapid successive merging of numerous smaller black holes in a very dense early universe, fueled by the frequent collisions and chaotic dynamics of nascent galaxies. These findings suggest that the relationship between galaxy formation and black hole growth might be far more intertwined and rapid than previously thought, making the origins of these cosmic monsters an even more thrilling frontier of research. It is a mystery that promises to continue rewriting our understanding of the universe's earliest, most dramatic acts. Imagine for a moment an era cloaked in a profound, ineffable quiet, the vast expanse of the cosmic dark ages. Yet even as the freed photons of the cosmic microwave background streamed away, leaving behind a cosmos dominated by neutral hydrogen and helium, the universe was far from inert. Hidden within the silent embrace of dark matter, halos, the seeds of future grandeur, were slowly germinating. But what followed the reign of the primordial population 3 behemoths, those colossal short-lived pioneers, remained a tantalizing enigma. Our most powerful optical telescopes, even the venerable Hubble, could only offer glimpses of what lay behind the impenetrable cosmic veil. The earliest stellar nurseries, the true engines of the universe's chemical transformation after the very first stars had exploded, remained largely obscured, cloaked in vast shrouds of newly formed dust and the immense redshift that stretched their faint early light into wavelengths our instruments struggled to capture. It was a missing piece, a profound blank in the universe's epic autobiography. Then, around 2 years ago, a golden eye opened, peering deeper, seeing farther, and seeing more clearly than anything before it. The James Webb Space Telescope, with its gargantuan 6.5-meter golden mirror, designed not for the visible spectrum, but for the stretched ancient light of the infrared, pierced through this primeval obscurity. It cut through the cosmic dust and the redshift like a precisely aimed laser through mist. What it unveiled was not the quiet, slow, gradual unfurling we might have theorized, but a universe ablaze with a furious, almost unimaginable rate of creation. The early galaxies, those nascent, irregular proto-galaxies that were the building blocks of the cosmic web, nestled within the invisible embrace of their dark matter scaffolds, were not merely forming stars. They were churning them out at a breakneck pace. These distant stellar factories, fueled by an almost inexhaustible supply of cold, pristine gas, gravitationally drawn into their burgeoning cores, were birthing new suns at rates that defy comprehension from our modern perspective. Consider our own Milky Way, a grand, majestic spiral, a serene galactic city that gracefully forms perhaps 1 or 2 new stars a year. Now behold the early universe galaxies in their fiery youth, raw and chaotic, igniting hundreds, even thousands of stars annually. This was a period of astonishing, almost violent efficiency, a grand cosmic assembly line operating at speeds that rewrite our textbooks on galactic evolution. This era, occurring within the first billion years after the Big Bang, was the universe's most prolific phase of starbirth, a period of unparalleled cosmic productivity. It was here in these superproductive, turbulent crucibles that the universe performed its most vital alchemy. While the first population 3 stars had exploded in titanic blasts, scattering the initial traces of light elements heavier than helium, the very first, metals, these subsequent generations of stars born in these rapidly evolving stellar factories, truly began to synthesize the vast majority of carbon, oxygen, nitrogen, and iron. These are the elements that form the very foundation of planets' complex chemistry and ultimately life itself. Every atom of oxygen we breathe, every speck of iron that courses through our blood, every carbon atom that forms the intricate backbone of organic molecules owes its existence to these ancient, furiously productive stellar foundries. They were the elemental cauldrons that transformed a universe of elegant simplicity into one of breathtaking complexity. The sheer abundance of cold gas, the universe's raw material, continuously replenished and drawn in by the unseen, inexorable tug of the dark matter scaffolding, allowed for this unparalleled period of star formation. These galaxies were not merely building blocks in a static architectural plan. They were dynamic engines of profound chemical enrichment, tirelessly working to infuse the cosmos with the ingredients for greater diversity. JWST allows us to witness this tumultuous, beautiful process with unprecedented clarity, providing a profound, almost sacred glimpse into the precise, intense conditions that allowed these initial titanic bursts of stellar ignition to occur. It's a testament to the universe's unyielding drive towards complexity, a dramatic revelation that illuminates how the very environment for rocky planets, and eventually for the emergence of biological systems, was not merely established, but furiously forged, laying the groundwork for all that would follow. The universe in its youth was not just expanding into a vast emptiness. It was furiously alive, actively creating the very elements of its future, echoing the ineluctable march of time. After tracing the universe's epic journey from the ineffable quiet before creation, through the Big Bang's shattering genesis, the inflationary whisper, the forging of lightness, and the long dark ages, we arrive at the grand, intricate tapestry of the cosmic web. We have mapped our cosmic address, felt the pull of the great attractor, pondered the axis of evil, and witnessed the relentless push of dark energy accelerate the cosmos towards an unknown future. Yet amidst this breathtaking saga of galaxies and stars, perhaps the most profound question whispers from the depths of the universe, echoing from every corner of existence. Are we alone? This isn't merely a philosophical query, but a silent, cosmic inquiry that has resonated through human consciousness for millennia, the ultimate frontier, not just of space, but of being itself. The scientific endeavor to answer this existential question falls under the umbrella of astrobiology, a field that synthesizes cosmology, biology, chemistry, and geology. It's a quest not for direct observation of alien organisms, for such an encounter is likely beyond our immediate reach across interstellar distances, but for detecting what we call biosignatures. These are not explicit sightings of life itself, but rather chemical fossils, or indicators that, when observed strongly, suggest biological activity. Imagine looking for a distant campfire across a vast, dark plain. You might not see the dancing flames themselves, but you could detect the subtle tendrils of smoke rising against the twilight sky, or the unique chemical fingerprint of combustion carried on the breeze. Similarly, astrobiologists seek these subtle, indirect hints. Biosignatures can take many forms, each a tiny clue in the universe's grand puzzle. They might be specific isotope ratios found in ancient rock formations on an exoplanet, deviations from expected geological abundances that point to biological processes at work. Or they could manifest as the presence of complex organic molecules in planetary atmospheres or on planetary surfaces, molecules whose intricate structures are exceedingly difficult for non-biological processes to form spontaneously in significant quantities. But perhaps the most compelling and actively sought-after class of biosignatures involves atmospheric disequilibria. This is where the universe, in its apparent simplicity, reveals its potential for astonishing complexity. Consider a planetary atmosphere that exhibits a persistent large-scale coexistence of highly reactive gases, such as vast amounts of oxygen and methane. On Earth, our vibrant biosphere tirelessly produces. These gases, oxygen is overwhelmingly generated by photosynthesis from plants and cyanobacteria, while methane is primarily produced by microbial life. These two gases are like chemical adversaries. They naturally react with each other, and left to geological processes alone, would quickly deplete from the atmosphere. Their sustained presence in significant quantities therefore represents a profound chemical imbalance, a state of disequilibrium that geology struggles to explain. It is the universe's quiet whisper of life. It implies a constant, powerful source regenerating these reactive components, a source that, based on our understanding of planetary physics and chemistry, is almost certainly biological. The quest for these subtle hints is at the absolute forefront of modern space exploration. Telescopes like the James Webb Space Telescope, our golden eye, which has already rewritten the early chapters of galactic formation by peering through cosmic dust to reveal hidden stellar factories and early black holes, are now being poised to help in this grand search. JWST's unparalleled infrared vision is perfectly suited to dissect the faint red-shifted light from the atmospheres of distant exoplanets searching for those telltale chemical anomalies. Future missions are being designed with even greater sensitivity, dedicated to analyzing the spectral fingerprints of these faraway worlds. Each new exoplanet discovery becomes a potential laboratory, a new canvas, where the brushstrokes of life might just be waiting to be deciphered. The possibility that a specific chemical blend in a distant atmosphere, a mere whisper in the vast cosmic expanse, could unravel the profound complexity of a living world, embodies the universe's stunning capacity for self-organization, from the grand cosmic web down to the delicate balance of planetary biochemistry. It is the invisible architect, the same patient force of gravity, that built galaxies, now hinting at the even more intricate architecture of life. The answer to "Are we alone?" remains elusive, yet the pursuit itself transforms us. It forces us to reconsider our place within the grand unfolding story, to embrace the unfathomable vastness and the myriad possibilities it holds. The cosmic journey continues, not just outward into the accelerating void, but inward towards the ultimate question of connection consciousness and what it truly means to be a living, breathing part of the universe. Humanity, now armed with golden eyes and an insatiable curiosity, is finally listening for the universe's most patient, persistent conversation. Imagine a world born of cosmic debris hammered by asteroids, its surface a molten, roiling hellscape under a sky thick with volcanic gases. This was Earth, billions of years ago, an alien realm utterly unrecognizable to human eyes. No blue oceans, no verdant continents, no breathable air. It was a crucible echoing the turbulent infancy of the universe itself, where elements forged in ancient stars coalesced into a nascent planet. This hostile solitude persisted for hundreds of millions of years, a silent testament to cosmic processes. Yet within this seemingly inert desolation, life began its improbable whisper. Not with grand multicellular forms, but with microscopic pioneers, single-celled organisms, the simplest architects of existence. For nearly 2 billion years, these tiny, unseen entities dominated, transforming the very planet around them. Their legacy is etched in time, preserved in geological formations called stromatolites, layered fossilized mats formed by colonies of ancient cyanobacteria. These dome-like structures, still found in isolated pockets today, are the primordial blueprints of biological activity, telling a story of life's earliest, almost unfathomable marks on a world. They are the first enduring biosignatures, a testament to the fact that even the most elemental life can leave an indelible fossil of its presence, awaiting discovery across cosmic distances. But the most dramatic transformation was yet to come, a planetary revolution spurred by the quiet, tireless work of these microbial titans. For eons, Earth's atmosphere was largely anoxic, a suffocating blend of nitrogen, carbon dioxide, and methane, devoid of free oxygen. Then, around 2.4 billion years ago, a profound shift began. The cyanobacteria, masters of a new alchemical art, photosynthesis, started harnessing the sun's energy, taking in carbon dioxide and water, and releasing oxygen as a waste product. Slowly, inexorably, this vital gas accumulated, first dissolving into the oceans, rusting iron deposits into the distinctive red bands seen in ancient rocks, before finally bubbling into the atmosphere. This was the Great Oxidation Event, a cosmic-scale terraforming project. It was not a gentle transition. For the anaerobic life forms that had thrived in the oxygen-free world, this atmospheric change was a cataclysm, a planetary poisoning that led to mass extinctions on an unimaginable scale. Yet this very catastrophe paved the way for something grander. Oxygen, once a poison, became the key to unlocking vastly more efficient energy production, fueling the eventual explosion of complex multicellular life. From simple microbes to sophisticated organisms, Earth's biology and geology became inextricably intertwined, a dance of coevolution. Our planet became a living laboratory, enduring cataclysms like snowball Earth events, periods of intense volcanism, and cycles of warming and cooling, each challenge shaping the crucible of life. The recurring motif of the universe as a dynamic canvas finds its micro-reflection here on our own world. Earth's long journey, marked by dramatic climate shifts and devastating mass extinctions, where 90% or more of all species vanished, is not merely historical curiosity. It is a profound guide. It teaches us about the resilience of life, the narrow tolerances required for its emergence, and the environmental conditions that support its persistence. The very signatures we seek on distant exoplanets, the atmospheric disequilibria. Chapter 31, that might hint at alien biology, are profoundly informed by the radical transformation Earth underwent. By studying our own world's tumultuous past, we gain invaluable insights into the whispers of life that might echo from distant, accelerating cosmos. Earth's story, from its primordial void to its vibrant present, is the closest thing we have to a Rosetta Stone for astrobiology. It offers a blueprint for what to look for, reminding us that the simple can lead to the complex, and that the long, patient work of unseen forces, biological and geological, can transform a planetary canvas. Our cosmic address, this blue marble, holds the key to understanding the profound question, are we alone? It is here in our own planetary home that the whispers of life become a roaring symphony, providing the very context for our search across the boundless void. The red dust swirled a perpetual whisper across a desolate ancient seabed. Dr. Alara Vance, eyes alight with curiosity, zoomed in on the panoramic image from Jezero crater. She saw the faint telltale layers, the dried river delta, and imagined the ripple marks of water that once flowed freely billions of years ago. It was a phantom ocean, a memory etched into the very stones of Mars, a silent testament to a past utterly unlike its stark, cold present. For centuries, humanity had gazed upon our nearest celestial neighbor Mars, not merely as another world, but as a tantalizing mirror reflecting our deepest questions about life's cosmic reach. What if life, that improbable dance of carbon and water, wasn't unique to our pale blue dot forged in elements scattered by the first stars, as Chapter 14 described? The ancient landscape of Mars itself whispered of a different time, a warmer, wetter epoch, billions of years ago, a primordial era when vast liquid water oceans might have gleamed under a thicker atmosphere, when rivers carved intricate pathways across its ruddy surface. Geologists have unearthed compelling evidence, ancient shorelines, vast floodplains, and mineral deposits that only form in the prolonged presence of standing water. This speaks of a Mars that was once vibrant, dynamic, perhaps even hospitable, a dramatic counterpoint to Earth's own turbulent evolutionary story, where life as explored in Chapter 32 profoundly reshaped a planetary environment. A time, perhaps, when microscopic life could have thrived in those fleeting, watery havens. Today, Mars is a cold, dry, seemingly barren desert, its thin atmosphere offering little protection from cosmic radiation. But the whispers persist, carried on the thin Martian winds, and more profoundly emanating from its very geological depths. One such whisper, a profound and perplexing one, has come in the form of fleeting seasonal plumes of methane detected in the planet's tenuous atmosphere. This discovery, made by ground-based telescopes and orbiting spacecraft, sparked intense scientific debate. Methane, that deceptively simple molecule, is a double-edged sword for astrobiologists, a quintessential example of the simplicity versus complexity paradox that defines cosmic inquiry. On Earth, it can be a clear biosignature, a gaseous exhalation from the very breath of life itself, produced by methanogenic microbes burrowing deep beneath the surface. Yet it can also arise from purely geological processes, subterranean volcanism, hydrothermal activity, or the serpentinization of certain minerals. The sporadic nature and localized sources only deepen the enigma, a persistent background, periodic venting, or something hinting at an active hidden biosphere. The question of its origin on Mars remains a profound cosmic riddle, a challenge to our very intuition about life's boundaries, fueling the scientific quest, with an almost unbearable tension embodying the very essence of the whispers of life motif that drives our search. To unravel this Martian mystery, humanity has sent its most sophisticated emissaries instruments designed to detect subtle biosignatures, as discussed in Chapter 31. Among them, NASA's Perseverance rover, a marvel of engineering and patience, tirelessly drills and collects core samples in the very heart of the Jezero crater. This specific site, an ancient lakebed and river delta system, was chosen with meticulous care because it indicates a long-lived water environment billions of years ago. It's exactly where water minerals and energy might have converged for life's emergence, or its fossilized remnants to endure. Perseverance is meticulously seeking not just the presence of water, but the faintest echo of past existence, ancient biomarkers, and chemical fossils. These are the indelible imprints, microscopic residues, or unique molecular structures, like complex organic compounds or specific isotopic ratios, that could serve as direct evidence of microbial life that might have flourished billions of years ago before Mars's dramatic transformation into the planetary relic we see today. These precious samples, carefully sealed in titanium tubes, await return to Earth for unparalleled laboratory analysis, a painstaking endeavor reflecting humanity's relentless pursuit of knowledge. The very goal of this ambitious endeavor is not merely to discover life, but to understand if it ever took root there, and if so, what its legacy might be for the wider cosmic narrative. What story would those Martian microbes tell about the universe's capacity for genesis, its profound ability to foster complexity from raw ingredients forged in stellar furnaces? Would it suggest life is common, arising whenever conditions are suitable? Or would it underscore the unique confluence of factors that led to life on Earth? The red planet, a silent sentinel, continues to hold its secrets close, its enigmatic silence challenging us to look deeper. But humanity's persistent, insatiable curiosity, born from those same cosmic forces that forged stars and galaxies, a curiosity that propelled us to understand the Big Bang's echo in the CMB, and the accelerating cosmos keeps turning over every dust-covered Martian rock, listening for that faintest whisper of life beyond our own, charting our true cosmic address in a universe teeming with possibility. The surface of Europa, stark and unforgiving, stretches like a colossal fractured mirror under the baleful gaze of Jupiter. Imagine for a moment the relentless chill, the ceaseless radiation bombardment. It is a world seemingly devoid of warmth, a celestial marble encased in a shell of impenetrable ice, scarred by tectonic stresses and ancient impacts. Yet beneath this frigid alien crust, a secret of unimaginable magnitude is believed to reside, a liquid heart beating silently in the darkness. To behold it, we must journey beyond the familiar past, the red planet's arid plains, and into the deeper reaches of our solar system, where the true enigma of extraterrestrial life might truly stir. This is not a whisper, but a profound, almost certain truth. Europa, one of Jupiter's Galilean moons, harbors a vast global ocean of salty liquid water, warmed not by a distant star, but by the relentless, kneading gravitational tug of its colossal parent planet. The dance of Europa around Jupiter is a cosmic ballet of immense power. Just as our own moon pulls at Earth's oceans, Jupiter's immense gravity exerts a powerful tidal force on Europa. As the moon orbits, its elliptical path causes the gravitational pull to vary, flexing and stretching its icy body. This continuous internal friction, this ceaseless cosmic massage, generates enough heat to prevent the deep subterranean water from freezing solid. It's an engine of warmth in an otherwise desolate realm, a hidden furnace powering the potential for life. Scientists postulate that this ocean, estimated to be more than 100 kilometers deep, far deeper than any ocean on Earth, could harbor hydrothermal vents on its seafloor, much like the black smokers found in Earth's abyssal depths. These vents, spewing forth mineral-rich superheated water, provide chemical energy, creating vibrant ecosystems teeming with life in the absence of sunlight. On Earth, these oases of life prove that sunlight is not a prerequisite for biological flourishing. Chemical energy, too, can fuel an entire biosphere. To unravel the secrets held beneath Europa's cosmic veil, humanity is dispatching a golden eye of its own, NASA's Europa Clipper mission. Set to launch later this decade, this robotic Voyager will not land, but will perform dozens of close flybys, swooping low over the moon's fractured surface. Its array of sophisticated instruments, including powerful radar that can peer through the ice, will map the ocean's depth and salinity, searching for active geological processes. But perhaps its most tantalizing quest is the hunt for plumes, geysers of water vapor and ice particles erupting from cracks in the moon's crust, potentially bringing pristine material from the subsurface ocean directly into space. If these plumes exist, Europa Clipper could sample them, analyzing the chemical composition for biosignatures, for those subtle whispers of life, without ever having to drill through miles of ice. It's a testament to our ingenuity, this tireless pursuit of knowledge chasing a ghost. Yet Europa is but one paradigm. Farther still past the majestic ringed jewel of Saturn, another world of staggering otherworldly beauty awaits Titan. This moon challenges our very definition of what a habitable world might entail. Unlike Europa's hidden ocean of water, Titan is a world cloaked in a dense orange nitrogen atmosphere thicker than Earth's, and on its surface, lakes and rivers not of water, but of liquid methane and ethane flowing across a landscape carved by cryovolcanoes that erupt icy slush instead of molten rock. The presence of complex organic chemistry in such abundance, fueled by the sun's ultraviolet light interacting with its atmosphere, makes Titan a colossal natural laboratory for prebiotic chemistry. It's a snapshot of what Earth might have been like billions of years ago, a primordial soup on a planetary scale. To explore this utterly alien yet chemically rich landscape, humanity has conceived the Dragonfly mission. This revolutionary drone-like rotorcraft, a marvel of engineering, will fly through Titan's dense atmosphere, hopping from location to location, sampling its dunes, its riverbeds, and the sites of its mysterious cryovolcanoes. It will search not necessarily for life itself, but for the very precursors to life. The complex organic molecules, the amino acids, the building blocks that formed on Earth before life truly took hold. Dragonfly will evaluate Titan's habitability from a completely different perspective, forcing us to consider if life in its boundless ingenuity could truly flourish in a world where water is as hard as rock and liquids are derived from natural gas. These icy worlds with their hidden seas and exotic chemistries represent not just destinations, but profound intellectual challenges to our Earth-centric view of life. They compel us to expand our imagination, to redefine the very conditions under which life might emerge and thrive. They are a silent testament to the universe's boundless capacity for wonder, an invitation to continue our cosmic quest, unraveling the cosmic narrative, one profound mystery at a time. The universe, it seems, holds an infinite array of possibilities for the emergence of life, far beyond the confines of our blue marble. The journey continues, always driven by the profound yearning to understand our place in this unfolding saga. The universe, a tapestry of creation woven over billions of years, from the silent void to the accelerating cosmos, has relentlessly posed its grandest question: are we inhabitants of this pale blue dot truly alone? After charting the birth of stars, the forge of elements, and the scaffolding of galaxies, our gaze now turns outward beyond our familiar solar system to contemplate the potential for life on worlds undreamed of just a generation ago. It is a quest that hinges on a singular fundamental concept, the habitable zone. Imagine, if you will, a delicate cosmic Goldilocks principle. Not too hot, not too cold, but just right for the most vital ingredient for life as we know it, liquid water. The habitable zone, often called the circumstellar habitable zone, or simply HZ, defines the orbital sweet spot around a star where temperatures allow water to exist in its liquid state on a planet's surface. Too close and water boils away into vapor. Too far, and it freezes solid, locked away as ice. This deceptively simple concept holds the key to unlocking countless mysteries. For millennia, humanity could only ponder other stars as distant points of light. Then a revolution struck. In recent decades, our astronomical instruments, keen as the keenest falcon, have unveiled a spectacular menagerie of exoplanets, worlds orbiting stars beyond our sun. What began as a trickle of isolated discoveries has swelled into an avalanche, with thousands now confirmed, each new detection deepening our sense of cosmic scale and potential. And among this burgeoning cosmic population are some truly tantalizing candidates residing squarely within their parent star's habitable zones. Consider Proxima Centauri, be a world that orbits Proxima Centauri, our very closest stellar neighbor, a mere 4 light-years away. This small red dwarf star, though dim compared to our Sun, nonetheless possesses its own delicate life-sustaining bubble. Proxima Centauri, be a rocky world slightly more massive than Earth, lies within this precise Goldilocks region. To stand on its surface, looking up at a star that glows not with the brilliant yellow of our Sun, but with a cooler red hue, is to imagine a truly alien sunrise, yet one perhaps warm enough for liquid oceans. The proximity of this world makes it a prime target for future study, a beacon of hope in the endless night. Further afield, a system of profound wonder unfurled before our eyes, TRAPPIST-1. This extraordinary arrangement, a mere 39 light-years distant, boasts not 1 but 7 Earth-sized planets, all tightly packed around their ultra-cool dwarf star. 3 of these 7 worlds, TRAPPIST-1, E, F, and G, reside comfortably within the star's habitable zone. Envision a cosmic ballet of 7 sisters potentially sharing a sky, each a possible realm for liquid water, and thus potentially for life. This discovery amplified the universe's quiet whispers of life, transforming them into a resounding chorus of possibility. Yet, as with all grand scientific narratives, simplicity often masks profound complexity. While being within the habitable zone is a crucial prerequisite, it is by no means a guarantee of life. A planet's atmospheric composition, its geological activity, the presence of a protective magnetic field against stellar radiation, and even the very nature of its host star. These myriad factors must align in a cosmic symphony for life to truly take hold and flourish. The universe's secrets are never easily surrendered. This complexity compels us to refine our search. Astronomers armed with tools like the magnificent James Webb Space Telescope, our golden eye designed to peer into the universe's deepest secrets, as explored in Chapter 27, are developing advanced techniques to seek those elusive biosignatures. As exoplanets transit or pass in front of their host stars, the starlight filters through their atmospheres. By analyzing the subtle shifts in the light's spectrum, its reflectance spectra, we can deduce the chemical composition of that alien sky, the detection of atmospheric disequilibria, such as the simultaneous presence of oxygen and methane, as discussed in Chapter 31's exploration of Earth's own story, would be a chemical fingerprint of immense significance, a potential smoking gun for biological processes. And beyond the chemical whispers, some dare to listen for something more direct techno-signatures. These are the potential signs of advanced technology, like repeating radio signals, laser emissions, or even anomalous energy consumption that might betray the presence of intelligent civilizations across the interstellar void. It is a long shot, a search for a needle in a cosmic haystack of unimaginable proportions, yet it is a testament to humanity's indomitable curiosity and our profound yearning to connect with something beyond ourselves. The accelerating cosmos, as detailed in Chapter 25, is a universe of accelerating distances, but it is also a universe of accelerating discovery. With every new exoplanet confirmed, every faint spectral line analyzed, every silent radio frequency scanned, we inch closer to answering the question that echoes through the ages. The possibilities, vast as the cosmic web itself, stretch infinitely before us, beckoning us to continue our grand exploration into the unknown. We are but a nascent intelligence, cradled within the Laniakea supercluster, listening, watching, and forever wondering if the silent, boundless void holds other forms of life, other stories waiting to unfold. Can anything truly be infinite? Or are there, even in the boundless expanse of the cosmos, fundamental limits to structure boundaries beyond which the grand design smooths into an undifferentiated sea? We have journeyed through the universe's fiery birth, witnessed the patient architect of gravity sculpt the primordial gas, and seen the invisible hand of dark matter weave the intricate cosmic web, an awe-inspiring tapestry of galaxies, clusters, and superclusters. We've mapped our own humble cosmic address nestled within the Laniakea supercluster, feeling the inexorable tug of the great attractor, and even grappled with perplexing anomalies like the axis of evil that hint at deeper mysteries. But what if all this breathtaking hierarchical organization has an upper bound? For all its profound complexity, for all the clustered grandeur of its filaments and superclusters, the universe, when viewed on truly colossal scales, appears remarkably, almost deceptively simple. Beyond a certain conceptual boundary, roughly 1 billion light-years. In extent, the cosmos exhibits an astonishing uniformity. This is the realm cosmologists refer to as the end of greatness, a poetic term marking the scale where the universe ceases to aggregate into ever larger gravitationally bound structures. It's the point where the clumpiness, the magnificent cosmic architecture that defines galaxies and clusters, gives way to a pervasive homogeneity. This isn't to say that the intricate cosmic web we discussed, born from the gravitational amplification of those initial quantum fluctuations and guided by the silent influence of dark matter, doesn't exist. Far from it. That magnificent structure is very real, the grand result of gravity's patient, inexorable work on scales up to hundreds of millions of light-years. But beyond that scale, the universe smooths out. It's a profound testament to the delicate balance of cosmic forces. While gravity tirelessly works to pull matter together, creating dense pockets of galaxies, the relentless expansion of spacetime itself, supercharged by the enigmatic push of dark energy, acts as a counterweight. On these unimaginably vast scales, the repulsive force of dark energy, the dominant power in the universe's current epoch, overcomes gravity's pull, preventing the formation of structures larger than approximately 1 billion light-years. This transition from clumpiness to homogeneity is a cornerstone of our modern cosmological models, a crucial observational pillar supporting the cosmological principle. The idea that the universe on large scales is both homogeneous and isotropic, looking roughly the same in all directions and at all locations. It's why the cosmic microwave background, the universe's baby picture, is so remarkably uniform, its tiny fluctuations merely the seeds of the structures that would grow over billions of years, but never beyond this ultimate limit. The universe in its grandest vista becomes a uniform expanding sea of galaxies, each receding from the other at an ever-increasing rate. The end of greatness serves as a profound reminder that even the most colossal cosmic structures adhere to fundamental physical limits shaped by the interplay of gravity and the accelerating expansion of space itself. It is a revelation that simultaneously simplifies and deepens our understanding of the universe's fundamental architecture, revealing a balance between chaos and order on the grandest scales, and inviting us to marvel at the elegant simplicity hidden beneath the dazzling complexity of our cosmic home. Imagine a grand cosmic symphony billions of years in the making, where the movements of galaxies and the birth of stars are choreographed with breathtaking precision. What invisible maestro conducts this immense performance? What force unseen and untouchable has shaped the universe from a formless void into the intricate cosmic web we inhabit. The answer time and again points to the profound, quiet power of gravity, and specifically to the enduring enigma that is dark matter. From the roaring inferno of the Big Bang, through the silent cosmic dark ages, and into the vibrant tapestry of galaxies, gravity has been the paramount sculptor. But it was not merely the familiar pull of atoms and light. As we explored in Chapter 10, the universe is dominated by a ghost in the machine, dark matter, comprising roughly 27% of its total mass energy. It neither shines nor scatters light. Its existence is inferred solely through its irresistible gravitational tug. Without this pervasive, invisible architect, our cosmos would be an utterly alien place, a diffuse, featureless expanse with no concentrated structures, no galaxies, no stars, and certainly no life. The very notion of our universe as a structured entity hinges entirely on its presence. The enduring significance of dark matter began in the universe's earliest moments. Those infinitesimal quantum fluctuations, mere ripples in the fabric of space-time, left over from the inflationary epoch, the whispers of possibility discussed in Chapter 9, were the original seeds of structure. But how did these microscopic jitters grow into colossal superclusters spanning hundreds of millions of light-years? Here dark matter played its decisive role, acting as the ultimate amplifier. Unlike ordinary baryonic matter, which was constantly buffeted by the intense radiation and pressure of the early universe, dark matter is collisionless and cold. It felt only the pull of gravity unimpeded by other forces. This crucial distinction meant that as the universe expanded and cooled, dark matter was able to clump together first unhindered by electromagnetic forces or radiation pressure that would have dispersed the baryonic matter. These nascent dark matter halos forming an invisible gravitational scaffold, as detailed in Chapter 11, acted like cosmic magnets. They steadily pulled in the surrounding neutral hydrogen and helium gas, patiently accumulating more and more material. It was within these deepening gravitational wells concentrated by dark matter that the gas eventually became dense and hot enough for the first stars to ignite, breaking the long night of the Dark Ages and heralding the cosmic dawn. Without this pre-existing framework, the ordinary matter would have been too spread out, too diffuse, and too slow to collapse and form the grand galactic cities that populate the cosmic web. Even today, dark matter continues its silent, relentless work. It is the unseen glue that binds galaxies together, preventing them from flying apart due to their rapid rotation, as Vera Rubin's pioneering observations first hinted. It holds colossal clusters of galaxies in their collective embrace, ensuring their cohesion even as the universe's overall expansion, now driven by dark energy, pushes them ever further apart. The majestic Laniakea supercluster. Our very own cosmic address is a testament to the colossal gravitational structures that only dark matter's pervasive influence could forge. Even the mysterious great attractor, that unseen gravitational anomaly pulling our entire local group, is likely a titanic concentration of dark matter still shaping our neighborhood on a grand scale. Yet despite its undeniable and fundamental importance, the exact nature of dark matter remains one of cosmology's deepest mysteries, a profound challenge to our understanding. Is it a new, undiscovered fundamental particle, perhaps a weakly interacting massive particle that only interacts through gravity and the weak nuclear force? Or is it something even more exotic, hinting at subtle modifications to our understanding of gravity itself on cosmic scales, pushing the boundaries of Einstein's elegant theories? The universe's very existence in its structured, star-filled, life-supporting form hinges on this invisible component, forcing us to acknowledge that our grasp of the cosmos, for all its breathtaking advances, is still profoundly incomplete. It is a constant reminder of our cosmic humility, that the most impactful forces are often the least understood. The pursuit of dark matter is not merely an academic exercise, it is a quest to unravel the very blueprint of our universe. From highly sensitive underground laboratories searching for faint particle interactions to powerful orbiting observatories mapping its gravitational lensing effects, dedicated scientists like Dr. Ilara Vance and Professor Ben Carter dedicate their lives to solving this enduring enigma. They and we stand at the precipice of a new understanding seeking to pull back the veil on the unseen hand that has shaped everything from the largest superclusters to the tiny quantum seeds from which our own galaxy, our sun, and ultimately ourselves emerged. The universe continues to unfold its secrets, and this invisible architect holds perhaps the most profound among them. What greater story could there be than the universe's own saga, spanning billions of years, from a silence so profound even the concept of nothingness struggled to take root to the accelerating expansion we witness today. We, the fleeting observers on a mote of dust suspended in a sunbeam, have spent millennia gazing at the stars, transforming ancient myths into scientific marvels, unraveling threads in an infinite weave of space-time and matter. From the fleeting spark of the Big Bang's moment of becoming, where the universe burst forth as the very expansion of space itself, our cosmic journey began. We traced the inflationary whisper, an exponential surge that smoothed the primordial cosmos, laying the homogeneous foundation. We explored the Quark-gluon plasma, a seething, untamed soup of fundamental particles, and witnessed the forge of lightness as Big Bang nucleosynthesis created the universe's first hydrogen and helium, shaping its elemental recipe. Then came the long, opaque shroud of the cosmic veil, a dense fog that trapped light for 380,000 years before the dramatic Recombination unveiled the universe's baby picture, the cosmic microwave background, a relic of cosmic infancy. For hundreds of millions of years, the Dark Ages descended, a quiet interlude where no stars shone, yet the seeds of structure, tiny quantum fluctuations, began their slow gravitational work. Here, the invisible architect, dark matter, comprising 27% of the cosmos, exerted its influence, building the gravitational scaffold upon which the visible universe would eventually form. The cosmic dawn finally broke around 400 million years after the Big Bang, heralded by the birth of behemoths, the colossal population 3 stars. Their tragically short lives culminated in the first supernovae explosions of unimaginable power that forged and scattered the first metals, the heavier elements essential for planets and life, into the pristine interstellar medium, leading to the grand Reionization unveiling of the universe. With these ingredients, the building blocks of the cosmos, the first proto-galaxies began their chaotic cosmic dance, coalescing into the intricate sponge-like cosmic web. Richard Gott's vision, a vast structure stretching beyond the end of greatness, our cosmic address, within Laniakea, all under the great attractor, sway. But the universe held another profound surprise. After 5 billion years of cosmic recoil, slowing under gravity observations of distant supernovae revealed the astonishing truth of an accelerating cosmos driven by the enigma of dark energy. This silent, powerful force, making up 68% of the universe, now dictates its ultimate future's shadow, pushing galaxies apart at ever-increasing speeds, threatening a cold, lonely Big Freeze. To peer into these depths, humanity forged the golden eye, the James Webb Space Telescope. JWST's revolutionary infrared vision immediately began rewriting early chapters, revealing galaxies surprisingly mature and brighter than theoretical models predicted for such an early epoch. It illuminated black hole beginnings, showing these leviathans growing faster than imagined. And it unveiled stellar factories in the universe's infancy, churning out new suns at astonishing rates, providing clues about star and planetary formation. Amidst this grand tapestry, the profound question, whispers of life, are we alone? We study Earth's own story and the Martian mysteries, search icy worlds' hidden seas like Europa and Titan, and explore habitable zones around distant stars, seeking the subtle biosignatures of alien life. Yet despite all that we know, threads remain untangled in this infinite weave. What is dark energy? What is dark matter? This ghost in the machine, this unseen hand of gravity. What of the unsettling alignment of the axis of evil in the CMB challenging cosmic uniformity? Are there other universes beyond our observable horizon, or is life an inevitable consequence of cosmic evolution or a rare, precious miracle? The journey of discovery is far from over. Our understanding is finite, but our curiosity is boundless, pushing us forever to chase what lies beyond the edge of our current horizon, toward the profound, humbling unknown. And so, from the silent void that birthed everything through the furious dance of creation, the long night of the dark ages, and the dawn of the first stars, we have chronicled the universe's most ancient story. We've peered through JWST's golden eye, glimpsing galaxies blooming faster than thought possible, and black holes swelling into cosmic titans in the blink of a cosmic eye. We've grappled with the invisible hand of dark matter shaping the very cosmic web, and confronted the relentless, accelerating push of dark energy, a force silently dictating our ultimate destiny. But as with all great journeys of discovery, every answer only unveils a deeper mystery. We stand at the precipice of understanding, knowing that despite our incredible progress, the true nature of dark matter and dark energy remains unknown. The subtle, unsettling whisper of anomalies like the axis of evil continues to challenge our most fundamental assumptions about the universe's ultimate architecture. Our quest is far from over. The cosmos is a grand, unfolding narrative, and we as humanity are its curious chroniclers, forever pushing the boundaries of our intellectual horizon. The questions that remain are not deficits in our knowledge, but invitations to continue exploring, to marvel, and to seek. There are still mysteries out there, written in the stars, waiting for us to read their ancient script. Thank you for watching Astro Horizons. If you've been inspired by the epic tale of our universe and wish to join us on future journeys of discovery, don't forget to subscribe to Astro Horizons and hit the notification bell. Together, we will continue to explore what lies beyond the edge of what we know.